Beneath the stillness of night skies and the familiar phases of the moon lies a question that seems at once absurd and profound. How many numbers would it take to fully describe something as deceptively simple as the moon, to capture every crater carved by eons of relentless asteroid impacts, to map every ridge, valley, and subtle gradient of chemical composition across its surface? One would need thousands upon thousands of coordinates and measurements, and this is just for one small rocky satellite. Consider then a planet, a star, a nebula, or the grandeur of an entire galaxy. As we scale up, the quantity of data balloons from millions to billions to something bordering on infinity. Yet curiously, when we shift our gaze toward the most extreme singularities in the cosmos, black holes, we encounter an astonishing simplicity. No matter how colossal their size or how exotic their origin, every black hole can be fully described by only three numbers: its mass, its electric charge, and its angular momentum. Not 3,000, not 3 million, just 3. This startling economy of description challenges our deepest assumptions about how information behaves in the universe. Everything that goes into a black hole, from light to matter, to the most complex structures and patterns, is reduced at the event horizon to a mere trio of values. It does not matter whether the black hole was birthed from the collapse of a dying star, the gradual accretion of interstellar gas, or the hypothetical convergence of all human knowledge funneled into a single point. The end result is always the same. The details vanish behind a veil, replaced by this minimal signature. This strange equivalence unsettles the very idea of memory and identity on a cosmic scale. If so much complexity can collapse into so little information, then what does that say about the nature of information itself? Where does it go? Is it lost forever? Or does it persist in some hidden way we have yet to understand? The first glimmerings of this puzzle trace back to a most unexpected place, the contemplations of an 18th century clergyman, John Michell, a parish priest in England with a mind sharpened by mathematics and physics, lived in an era when gravity had recently been tamed by Newtonian theory. Light, then thought to be composed of particles, should in principle be subject to gravity like anything else. Michel pondered this idea with care. If one could throw an object upward with sufficient speed, it would escape the pull of Earth entirely. So what would happen, he asked, if an object were dense enough that its escape velocity exceeded the speed of light? No light could ever escape its grasp. It would be invisible, perfectly dark, known only by the weight of its presence. In the language of Newtonian mechanics, Michel had described what we would one day call a black hole, nearly 2 centuries before the name was coined. But his musings, while insightful, were cast aside for a long time. The physics of gravity slipped into relative obscurity as the 20th century dawned, eclipsed by the meteoric rise of quantum mechanics. Then, in the trenches of the First World War, a German soldier named Karl Schwarzschild found refuge from the violence by turning to Einstein's newly published theory of general relativity. Despite the chaos surrounding him, Schwarzschild derived a solution to Einstein's equations that described the space around a point mass. In this solution, there existed a critical radius where space-time warped so completely that escape became impossible. Later generations would call this the event horizon. Here was the modern mathematical foundation for black holes, discovered in the midst of one of humanity's darkest hours. Still, the concept remained an intellectual curiosity. a strange corner of theory with no clear observational counterpart. It would take the revolutions of the 1960s and 1970s to breathe life into these shadows. As the Cold War era brought new technologies and eyes to the sky, astronomers began to see the heavens in new light, literally. With the launch of X-ray telescopes above the atmospheric blur, researchers discovered strange celestial objects radiating furious amounts of energy from tiny, unseen sources. One in particular, known as Cygnus X1, defied explanation. The X-rays it emitted were far too energetic and localized to come from any known star. Something unseen was devouring matter, heating it until it blazed in invisible frequencies. A black hole, it seemed, was no longer theoretical. At the same time, theoretical physics was undergoing its own renaissance. A young British physicist named Stephen Hawking, newly diagnosed with a terminal illness, threw himself into the equations of relativity with fervent urgency. Alongside mathematician Roger Penrose, Hawking helped prove that the collapse of mass under gravity under quite general conditions would inevitably lead to a singularity, a point where the known laws of physics broke down. Black holes were not just possible, they were unavoidable. The universe, through its own natural processes, made them routinely. Yet even as observational evidence and theoretical rigor aligned to confirm black holes' reality, deeper questions emerged. Solutions to Einstein's equations suggested something eerie. All black holes, regardless of how they formed, seemed to settle into only a handful of types. The Schwarzschild black hole, uncharged and non-rotating. The Reissner-Nordstrom black hole, charged but static. And the Kerr black hole, which spun like a cosmic gyroscope. There were no other stable options. John Wheeler captured the strangeness of this with a now famous phrase, "Black holes have no hair." Gone were the details of formation, the patterns of infalling matter, the histories of the stars that birthed them. All that remained were those three numbers. This bizarre simplicity echoed something else in physics, the thermodynamic concept of entropy. In a gas, for instance, entropy reflects the number of microscopic configurations that correspond to a macroscopic state like temperature or pressure. The air in a room may feel uniform, but it is made of countless molecules zooming in all directions, their individual paths hidden. A higher entropy means more hidden complexity. Could something similar apply to black holes? Could their mass, charge, and spin be concealing a vast number of internal arrangements hidden from view behind the event horizon? In the early 1970s, Jacob Bekenstein dared to say yes. He proposed that black holes had entropy, and that it was proportional not to their volume, but to the area of their horizon. It was an odd claim, for entropy usually scaled with volume after all. A bigger room holds more air molecules, more microstates. But for black holes, the key seemed to be the surface. Stephen Hawking initially resisted the idea, yet through his own investigations, he uncovered something even stranger. Black holes, he found, radiated energy. They had a temperature, and if they had a temperature and entropy, then they obeyed the same laws as heat engines and gases and stars. They were thermodynamic objects after all. This radiation, now called Hawking radiation, emerges not from the black hole itself, but from the quantum vacuum just outside it. In the strange fog of quantum fluctuations, particles and antiparticles constantly pop in and out of existence. Normally, they annihilate quickly, leaving no trace. But near the event horizon, one particle might fall in while the other escapes. The escaping one becomes real, carrying away a sliver of the black hole's mass. Over unimaginable spans of time, this process could cause a black hole to evaporate entirely. But here lies a paradox. If the radiation is purely thermal random and featureless, then it carries no information about what fell into the black hole. The original complexity, the details of everything swallowed, would be gone. This violates a sacred principle of quantum mechanics that information is never truly destroyed. The tension between this principle and the apparent loss of information in black hole evaporation sparked one of the greatest debates in theoretical physics. Could information be somehow preserved? If so, where was it hiding? A clue came from the entropy itself, since it scaled with area, not volume. It hinted at a deeper truth, that the universe might be more like a hologram than a solid object. Just as a two-dimensional surface can encode a three-dimensional image, perhaps the surface of a black hole encodes all the information about its interior. This idea blossomed into the holographic principle, a radical proposal that all of the information in a region of space could be represented on its boundary. If true, this would not only resolve the information paradox, but also suggest a new way of thinking about space, gravity, and quantum mechanics. But the implications stretch even further. If the universe itself follows this holographic logic, then our three-dimensional reality may emerge from two-dimensional data inscribed on a distant boundary. The cosmos would be a projection, and what we perceive as solid ideal continuous space might be underpinned by abstract patterns of information. Black holes, in this view, are not just cosmic curiosities. They are the key to understanding the fundamental architecture of reality. And yet, despite all this progress, a final answer remains elusive. We do not yet know precisely how information is preserved in black hole evaporation. We cannot yet peer inside an event horizon. The singularities at their cores remain shrouded in mystery. What we do know is that black holes force us to confront the deepest questions about what it means to know something, to describe something, to preserve identity in a universe where even light cannot escape. They are both destroyers and preservers, both prisons of matter and gateways to understanding. And in the silence at their centers, they may hold the final secrets of space, time, and the human quest to know. To look into a black hole is to gaze at the universe's most disciplined eraser. All stories vanish there. Stars, planets, dreams, identities, equations, whatever crosses the threshold is rendered mute, its past stripped clean. Yet paradoxically, what lies beneath that silence is not absence, but the purest expression of presence. For black holes, as austere as they are in outward description, may contain the deepest reservoirs of hidden structure in all of physics, and perhaps more than any other phenomenon, they force us to ask, what does it mean to keep a secret in a universe built on information? While black holes may look like cosmic voids, they are anything but simple emptiness. Each one is defined by three and only three quantities: mass, electric charge, and spin. It seems absurd at first glance that a swirling storm of infalling matter, gravitational violence, and collapsed histories could be summed up so minimally. No texture, no detail, no footprint of origin survives. The shell around a black hole, called the event horizon, is where all the complexity stops. It is as if the cosmos itself declared everything past this line becomes irretrievable. All identities are redacted. But this simplicity is deceptive, for it conceals a puzzle that continues to haunt theoretical physics. Where does the rest of the story go? In the early stages of black hole theory, this question did not seem urgent. General relativity allowed for singularities, regions where the curvature of space-time became infinite and the normal rules of physics broke down. Mathematicians could handle this, after all. Infinities often appear in equations without always causing trouble. Yet once quantum mechanics entered the scene, the tension became unbearable. One theory insists on preserving information, while the other seems to hide or even destroy it. The incompatibility sharpened into a crisis. And at its center was the event horizon, that silent boundary where light is forbidden from returning and where meaning seems to vanish. As we explored further, it became clear that black holes were not merely anomalies. They were thermodynamic entities. Just as a kettle of boiling water can be described by its temperature and entropy, so too can a black hole. This comparison began as a metaphor. Then it hardened into mathematics. The entropy of a black hole is proportional not to its volume, as one might expect, but to the surface area of its event horizon. This one insight shattered traditional assumptions and whispered of a deeper logic that the contents of a region might be fully encoded on its boundary. Here was the seed of the holographic principle. To understand how revolutionary this idea was, imagine taking everything that ever fell into a black hole, a mountain, a planet, a library, an orchestra, an ocean of memories, and compressing all that informational complexity into a two-dimensional skin, the details of every scream, every sigh, every heartbeat reduced not into nothing, but into a flattened cipher etched on the horizon's surface. That information would be unrecognizable to us, like a song translated into a mosaic. But the theory suggests it would be there, hiding in the correlations, awaiting decipherment. Black holes, then, might be less like graves and more like vaults. Yet this vault has a leak. That leak is Hawking radiation, born from quantum fields just outside the event horizon. Because of Heisenberg's uncertainty principle, even the vacuum is restless. It seethes with temporary particle-antiparticle pairs that blink into being and vanish again. Most of the time, these pairs annihilate quickly, restoring the vacuum's balance. But near the event horizon, things can go differently. One particle can fall in while the other escapes. The escaping one becomes real, an emissary of the whole's fading energy. Over time, this radiation carries mass away. The black hole shrinks. This was a radical revelation. It meant black holes are not eternal. They evaporate. Given enough time, a mind-breaking span, vastly exceeding the current age of the universe, they dissolve into a wisp of radiation. But if that radiation is perfectly thermal, it cannot encode the specific information about what formed the black hole. All that fine detail would be lost. And this, according to quantum mechanics, is unacceptable. Information must always be conserved, not scrambled into irretrievable static. The problem deepens when we consider the entropy, since it scales with area and not volume. The horizon seems to play a much more active role than previously thought. In ordinary thermodynamics, entropy is a measure of hidden arrangements. A gas in a box might look calm, but it hides trillions of particle motions, each contributing to its overall disorder. The more possible configurations, the higher the entropy. For black holes, the entropy suggests an unfathomable number of possible internal states, but the only surface we are allowed to study is two-dimensional. It is like judging a library by the size of its front door. This led to the audacious proposal that black holes are holograms, not illusions, but systems whose full complexity is encoded on a boundary. The information that seems lost inside may actually reside on the event horizon itself, expressed in subtle quantum correlations. What appears to be a uniform surface might in fact shimmer with microstates, each reflecting a piece of the black hole's past. If true, this would preserve the principle of information conservation and uphold the tenets of quantum mechanics, all while reshaping our conception of space itself. In the 1990s, this idea matured into a formal framework known as the ADS-CFT correspondence, pioneered by physicist Juan Maldacena. Though highly abstract and rooted in esoteric mathematics, its implications are vast. It posits that a theory of gravity in a volume of space can be fully described by a non-gravitational theory on the boundary of that space. In other words, what happens in 3 dimensions can be projected onto 2. This is not science fiction. It is now a central pillar of theoretical physics. The universe, it seems, may be a grand projection, with reality as we perceive it being a kind of emergent illusion. Black holes offer the most dramatic stage on which this projection plays out. Their apparent paradoxes push our theories to their limits. They force us to grapple with contradictions that arise when quantum mechanics and general relativity are brought together. The surface of a black hole becomes not just a boundary, but a battleground. The outcome of this battle may reveal the true nature of reality itself. And yet, even now, we are left with questions. If black holes evaporate completely, and if the emitted radiation is subtly entangled in just the right way to preserve information, then it must carry a hidden pattern, one that is unimaginably complex, yet ultimately deterministic. But how can we decode that pattern, and more tantalizingly, could the same principle apply to the universe as a whole? After all, if the cosmos follows the rules of holography, then our own experience of space, time, and self may be projections from a deeper substrate: identity, memory, causality. All the features we take for granted may emerge from encoded information dancing on a distant boundary. In this view, black holes are not exceptions but exemplars. They are the clearest expression of the universe's hidden grammar, its unwritten laws made visible through paradox. The task now is to listen more closely, not to the light that black holes absorb, but to the faint whisper of what they might still be saying as they slowly evaporate. In that whisper may lie the traces of fallen stars, the echoes of long-dead civilizations, the imprint of order and chaos woven together at the edge of understanding. Each black hole is a story waiting to be told in a language we are only just beginning to decipher. Across the vast gallery of cosmic phenomena, few ideas strike us with such paradoxical clarity as the concept of a black hole. It is at once the end of knowledge and the beginning of mystery. From the outside, it offers no detail, no nuance, only gravity, an invitation to fall. But inside, or perhaps upon its very surface, lies something more provocative, a tangled ledger of cosmic memory. In this chapter of discovery, we do not seek new stars or galaxies. Instead, we descend into theory, into the structure of thought itself, following the threads that bind entropy, space, and information into the most compelling paradoxes the universe has ever posed. The trail begins not with telescopes, but with the laws of heat and disorder. Entropy, in classical physics, is a measure of how many ways a system can be internally configured without changing its outward appearance. A cold block of metal has low entropy. A cloud of hot gas has much more. Yet black holes, seemingly devoid of internal parts, still possess entropy more than most objects in the cosmos. How can this be? The answer lies in a strange realization that the surface area of a black hole, and not its volume, encodes its entropy. This single geometric oddity transforms our understanding of what a black hole is. It is not a void. It is a container of hidden order, projected onto a surface like a shadow that tells the full story of its source. The implications of this principle extend far beyond astrophysics. It invites a radical new view of space itself, that perhaps what we think of as a volume, be it a region of gas, a galaxy, or the entire observable universe, may be fundamentally defined by its boundary. This is the essence of the holographic principle, a proposal so sweeping that it challenges not only the geometry of space, but the architecture of physics itself. The world we perceive in 3 dimensions may, at a deeper level, emerge from information encoded in 2. For a while, this was just a beautiful thought. Then came AD/CFT correspondence, a theoretical bridge that connected gravity in a 5-dimensional spacetime to a 4-dimensional quantum theory without gravity. At first glance, this seemed like an abstract puzzle, confined to esoteric corners of string theory, but it offered something invaluable, a proof of principle. It showed that gravity itself, with all its curves and collapses, could be recast in terms of a quantum theory that lives on the edge. The implications were breathtaking. It meant that black holes and perhaps the universe are best understood not as things with insides and outsides, but as codes running on the edge of space. And yet, even with this elegant language, the question remains what happens to information inside a black hole. Stephen Hawking's calculations suggested that radiation from an evaporating black hole carried no trace of what fell in. It was pure heat, indistinct and irreversible. This seemed to violate a cornerstone of quantum mechanics, that all processes are, at their heart, reversible and deterministic. If a black hole completely evaporated, and all it left behind was undifferentiated radiation, then the past would be erased, not hidden destroyed. That conclusion shook physics to its core. Attempts to resolve this tension sparked decades of debate. Some theorists clung to the idea that information truly vanished, requiring a modification to quantum theory itself. Others suspected that the radiation might, in subtle ways, be correlated, that hidden within its statistical fog were fingerprints of the things that once fell in. But how could this be? A single particle of Hawking radiation is random. But perhaps the correlations emerge only when the full radiation history is taken together, like piecing together a sentence from scattered letters across a library of books. It is not the parts, but their relationships that encode the memory. This idea gained momentum with deeper investigations into entanglement. In quantum theory, particles can be linked in such a way that their properties are no longer individual, but shared. If one particle is measured, the outcome of its entangled partner is immediately affected, no matter how far apart they are. In the black hole context, entanglement might be the bridge between past and future, encoding information in the very correlations among the escaping radiation. The information isn't gone. It's woven into the structure of space-time itself. Meanwhile, theoretical breakthroughs gave physicists new tools to describe this entangled radiation. Page curves, named after Don Page, a collaborator of Hawking, suggested that if black holes preserve information, the entropy of their radiation should rise and then fall as the hole shrinks. For decades, this curve was speculative, but recent developments, using techniques from holography and quantum extremal surfaces, have begun to show how these curves might arise from first principles. The radiation becomes less random over time, meaning begins to re-emerge from chaos. These developments do not offer direct answers. We still cannot open a real black hole, sift through its interior, and retrieve the past. But they give us a growing sense that information is not lost, it is transcribed. And just as burned letters leave patterns in ash and heat, black holes may leave behind the very data they seem to destroy. Still, the question of black hole interiors lingers. What lies beyond the horizon, past the surface that no signal can cross? According to general relativity, there is a singularity at the center, an infinitesimal point where density and curvature become infinite. But this is a signal of breakdown, not of clarity. Infinite values mean the theory has reached its limit. Something new is required: a theory of quantum gravity, a unification of Einstein's spacetime and the probabilistic machinery of quantum fields. String theory offers one candidate. It replaces point-like particles with tiny vibrating strings, whose different modes correspond to the particles we observe. In some string-theoretic models, black holes are composed of branes and strings wrapped in intricate geometries. These models have succeeded in reproducing the entropy formula for certain types of idealized black holes. This suggests that, at least in these contexts, black holes can be made of identifiable microstates. They are not featureless pits, but highly ordered quantum systems. But these successes are limited. They apply to supersymmetric, highly symmetrical black holes in spacetimes unlike our own. Still, they hint at something more general. Perhaps all black holes, even the ones in our sky, are not singularities at all, but ensembles of quantum configurations. Perhaps the singularity is an illusion, a mirage that arises when we apply classical concepts where quantum ones should reign. Some researchers propose that the true structure of black holes involves a firewall, a searing layer of quantum disruption at the event horizon, where entanglement breaks down. Others suggest that space-time is more interconnected than we thought, with wormhole-like bridges that encode entanglement as geometry. These ideas are speculative, but they emerge from serious efforts to reconcile quantum theory and gravity, and they reveal the depth of the challenge before us. In all of this, the black hole remains central. It is no longer just a graveyard for stars. It is a laboratory for the laws of nature, a pressure point where our theories stretch and sometimes tear. From entropy and holography to entanglement and quantum gravity, the black hole is the crucible in which the future of physics is forged. And yet, for all their conceptual weight, black holes are also real things in the sky. They spin, they collide, they shape galaxies. They influence the lives of stars and stir the centers of galaxies into bright quasars. Some are small, born from dying stars. Others are giants, billions of times more massive than the Sun, lurking at the hearts of distant galaxies. And as telescopes grow sharper, we have begun to see them more clearly. We have imaged the shadow of a black hole in the galaxy M87. We have measured gravitational waves from merging black holes a billion light-years away. These signals are not merely data. They are echoes from regions where space-time itself is warped beyond comprehension. With each observation, we peel back a layer of mystery. And with each new insight, we are reminded that the universe is not just stranger than we imagine, it is stranger than we can imagine. Perhaps that is what draws us to black holes again and again. They are thresholds, not just in physics, but in meaning. They beckon us with questions we do not yet know how to ask, and reward us with truths that change what we thought it meant to know anything at all. In their darkness, we find reflection. In their silence, we hear the resonance of all that we have yet to understand. In the shadowed depths of the universe, where light fails and space-time folds in upon itself, black holes loom as both a challenge and a promise. They are reminders that even in a cosmos governed by elegant equations, there remain boundaries, places where our understanding falters, where physics becomes poetry and speculation becomes necessity. But if particles and planets are objects, black holes are events, curved scripts in the theater of gravity. And just when we think we've unraveled their story, they write a new act beneath our feet. What makes a black hole so deceptively simple on the surface and so complex in its implications is that it keeps no record of its origins. It does not reflect on the identity of the star it once was. It tells us nothing about the galaxies whose matter it consumed or the cataclysms that forged it in the crucible of cosmic violence. Instead, it offers a minimalist resume: mass, spin, and charge. 3 numbers, no more. But from these numbers unfolds a physics so rich and intricate that it has become the front line of our search for a deeper theory of reality. One of the most perplexing aspects of black hole physics is that they emit radiation, Hawking radiation, a slow leaking of energy from an object defined by its ability to let nothing escape. This isn't emitted from the black hole's core, but from the quantum vacuum near its event horizon, where fluctuations give birth to particle-antiparticle pairs. One falls in, one flies out. Over time, this slow release chips away at the black hole's mass, like an iceberg sublimating in sunlight. Eventually, if left alone long enough, the black hole could vanish entirely. But this brings us face to face with the infamous information paradox. If everything that enters a black hole is eventually erased by this thermal radiation, then information is lost, a violation of quantum mechanics, where processes are supposed to be reversible, and no detail of the universe's evolution is ever truly deleted. The very core of quantum physics trembles before this question. How can we reconcile the irreversible fading of a black hole with the idea that the universe keeps perfect track of everything? One of the most promising answers lies in the realm of quantum entanglement. When black holes evaporate, they do not release isolated, independent particles like sparks from a dying fire. Instead, each particle is subtly entangled with its predecessors and successors, woven together by a tapestry of shared information. The pattern itself is inscrutable if you look only at a piece, but if you gather the whole of the emitted radiation, The entanglement among its parts may allow you to reconstruct the information thought to be lost. This idea gains strength from a deeper symmetry in physics, the holographic principle. If all the information about a black hole's interior can be encoded on its surface, then perhaps the same is true for the universe as a whole. What we experience as three-dimensional space might actually be the projection of a two-dimensional structure existing at the boundary of reality. It's as if the cosmos were a grand cinema, and everything we see, the planets, the stars, our memories are shadows cast on the screen by data written elsewhere. This is not merely metaphor. Mathematical formalisms like the ADS-CFT correspondence have demonstrated in precise terms that certain gravitational systems can be perfectly described by lower dimensional quantum theories without gravity. In these models, a black hole that forms, radiates, and evaporates still conserves information not in its volume, but in the quantum fields at the boundary. It is an astonishing convergence of disciplines: gravity, quantum mechanics, and information theory, all speaking the same language for the first time. And yet, mysteries endure. One of the most striking proposals to emerge in recent years is the concept of islands, regions of space, where information, thought to be lost, actually lingers. In quantum calculations that include gravity, it turns out that the entropy of radiation can be reduced by considering contributions from inside the black hole. These islands effectively act as hidden vaults, storing information that later leaks into the radiation stream. It's as though the black hole, even as it evaporates, whispers fragments of its past in every particle it releases. Parallel to these ideas runs a darker, stranger hypothesis, the firewall paradox. According to some interpretations, the smooth passage through the event horizon predicted by general relativity may not be so smooth after all. Instead, infalling observers might be incinerated by a wall of high-energy quanta, a rupture of space-time continuity caused by the breakdown of quantum entanglement. This is deeply unsettling, for it contradicts our long-standing belief in the principle of equivalence that an observer falling into a black hole would notice nothing unusual at the horizon. But perhaps, in this ultimate confrontation between gravity and quantum mechanics, even our most cherished principles must yield. As we ponder these paradoxes, we must remember that black holes are not merely thought experiments. They are real objects, woven into the structure of the universe, and their influence stretches far beyond their own horizons. In the centers of galaxies, supermassive black holes serve as anchors for spiraling arms and stellar orbits. In these places, matter churns into luminous accretion disks, emitting radiation so intense that it outshines the combined light of hundreds of billions of stars. These are quasars' cosmic lighthouses powered by the hunger of invisible giants. Black holes collide too, and when they do, the universe trembles. The gravitational waves they release ripple across space-time itself. Faint distortions that carry the story of their dance across eons and voids. Detectors like LIGO and Virgo have captured these tremors, allowing us to listen to the music of merging black holes. From these signals, we have inferred their masses, their spins, their moment of union. It is as if, in their final embrace, they send out one last transmission proof of their existence and a farewell. In recent years, we have gone beyond inference. We have begun to see them. The event Horizon Telescope, a globe-spanning array of radio observatories, gave us the first image of a black hole's shadow. It is not a picture in the ordinary sense, but a portrait composed of captured light bending around the event horizon, illuminating the space just outside the unseeable. In that dim halo lies the silhouette of a singularity, not just a black circle, but a window into the structure of reality. And still we wonder what lies within. If black holes are thermodynamic objects, what is their heat made of? If they are quantum systems, what are their fundamental bits? Are they woven from strings or brains or something not yet conceived? The truth is, we do not know. Our best tools, mathematics, measurement, imagination, have brought us to the edge, but the interior remains veiled. We circle the mystery, sketching its outline with theory and observation, but the center holds its silence. Perhaps the black hole is not a place, but a question, one so profound it reshapes the physics around it. It is the embodiment of limits, the limit of light, of time, of knowledge. But in confronting those limits, we grow. The black hole shows us that the universe is governed by principles deeper than the ones we first guessed, and that our quest to understand will always be one step behind what there is to know. What began as a curiosity in the mind of an 18th century clergyman has become the crucible of modern physics, from Newton to Einstein to Hawking, from entropy to entanglement to information. The black hole threads a line through the intellectual evolution of humanity. It is not just a thing that exists. It is a symbol of what it means to explore, to question, to wonder. And maybe, in the end, the reason black holes matter so much is not just because they are powerful or mysterious, but because they mirror our own search for meaning. We, too, are made of information. We, too, are trying to preserve what matters as we fall through time. The black hole, in its darkness, does not obliterate hope. It sharpens it. It dares us to look closer, to think deeper, to ask again. What if the universe has been trying to teach us something all along, not through clarity, but through contradiction, through objects so extreme they seem to defy reason itself? In our efforts to understand black holes, we have not only unraveled some of the strangest laws of physics, we have also come face to face with the boundaries of knowledge. And beyond those boundaries, we glimpse something even more humbling, the truth that understanding may require us to rethink everything we thought was solid. It begins with the problem of the inside. We can observe the light around a black hole. We can track its gravitational influence. We can even map the ring of radiation just outside the event horizon. But the interior, the true heart of the black hole, is beyond reach. Anything that crosses the threshold is lost to our instruments, cut off from the rest of the universe by a one-way membrane. Not because we lack the right tools, but because of the very structure of space-time. Time and space switch roles beyond the event horizon. Movement toward the singularity becomes as inevitable as moving into the future. This raises a question so strange it feels almost theological. Is the interior of a black hole real in any meaningful sense? If no outside observer can ever confirm it, does physics still apply in a region that can never be tested? These are not idle questions. They force us to confront the limits of science itself. Most of our theories are built on observation, repeatability, verification. But black holes hide their truths by design. And yet, They might also offer our best chance to unify the two great pillars of physics, general relativity and quantum mechanics, into a single, coherent picture of reality. That search has led us to some extraordinary ideas. Among them is the notion that the interior of a black hole is not an ordinary region of space, but a kind of encoding of information, an internal hologram shaped by quantum entanglement. According to this view, everything that falls into a black hole is stored not in the core, but smeared across the surface like a cosmic ledger. This ledger keeps track of every interaction, every infalling particle, every whisper of matter and energy. And though we can never open the book, its pages radiate out slowly through Hawking radiation, leaving clues in the patterns and correlations of those escaping photons. This perspective offers a startling possibility. What we experience as the inside of a black hole may actually be a mental construct, an emergent phenomenon arising from the entanglement between quantum states on the horizon. In other words, space-time itself, the very fabric of up and down, left and right, forward and back, might be a secondary property of something more fundamental, pure information. This idea has been championed by some of the most brilliant minds in theoretical physics, and though it remains speculative, it is reshaping how we think about reality. But even if we accept that the interior is real in this abstract way, we still do not know what it is made of. String theory has offered one route into the unknown. In highly symmetric universes with extra dimensions, it has provided mathematical models that let us count the microstates of certain idealized black holes, states that, together, account for the black hole's entropy exactly. These stringy configurations, built from vibrating loops and extended membranes, offer a glimpse of what the stuff inside might be. Not ordinary particles, but deeper entities that weave together gravity and quantum mechanics into a unified whole. Yet for all its beauty, string theory's predictions remain just beyond experimental reach. We cannot yet confirm the existence of strings, or brains, or the extra dimensions they require. But the mathematical success of these models gives hope. It suggests that black holes are not just endpoints, but gateways, portals to a deeper layer of physics that lies just beneath the surface of what we can see. This line of thought leads to an even more audacious idea that space and time themselves are not fundamental at all, that the universe is built not from fields and particles, but from networks of quantum information. In this picture, geometry arises from entanglement, and distance is a measure of how correlated two regions of space are. A black hole, then, is not a place in space. It is a disruption in the fabric of correlation, a region where the usual rules of connectivity break down, and when it evaporates, the pattern of those correlations shifts, like a rearrangement of notes in a symphony we cannot yet hear. But even this is not the end of the mystery, because black holes are not eternal. They age, they evaporate, and in doing so, they seem to undergo a transformation more profound than death, the transmutation of structure into signal. As the black hole shrinks, its temperature rises, its radiation intensifies, and in its final moments, it releases a flood of particles, rich in energy, but impoverished in meaning unless, that is, the pattern of those particles encodes the very memory of all that came before. This is the heart of the information paradox. If a black hole dies in silence, emitting only random thermal noise, then everything it swallowed is gone forever. Not just matter, but the information, the shape, the sequence, the story. This would mean that the universe itself is forgetful, that it suffers irreversible amnesia. But if, instead, the radiation is subtly structured, if it contains the fingerprints of every past infall, then information is conserved, and the black hole becomes a kind of cosmic server, slowly uploading its archive back into the universe, photon by photon. The debate is ongoing, but there are reasons to hope. Advances in quantum gravity, entanglement entropy, and holography suggest that the information is not truly lost, but scrambled, shuffled like cards in a deck, or encrypted in a code we do not yet understand. This raises another possibility that the universe itself is a computation, a vast and ongoing calculation that evolves according to physical rules, with black holes acting as processors, as nodes in a cosmic network. Seen this way, black holes are not monsters. They are archivists, compressors of data. They are not the end of stories, but the distillers of them. And the universe, in all its complexity, may be driven not by forces alone, but by the flow and transformation of information. It is an idea both exhilarating and unsettling, because it suggests that what we see, the stars, the galaxies, the motion of time, is just the interface. Beneath it lies code, not binary, not silicon, but something deeper, quantum logic, entangled fields, probabilistic flows. In such a world, meaning itself becomes physical. A black hole is meaningful not because it is massive, but because it contains and eventually reveals something about the universe that no other object does. And perhaps this is why we are drawn to them, not merely as scientists or storytellers, but as beings hungry for truth. The black hole challenges everything we believe about knowledge, that it can be preserved, that it can be accessed, that it can be trusted. It forces us to reckon with what it means to lose something forever, and what it means to recover it, if only in a different form. In the end, black holes are not just cosmic laboratories. They are mirrors. They reflect our greatest questions back at us. What is identity? What is time? Can anything truly be destroyed? Is there a boundary beyond which meaning fails, or is every ending just the beginning of another interpretation? We once looked to the stars and saw gods, myths, and monsters. Now we look again and see questions written in gravity, and among those questions, none are more profound than those posed by black holes. They are the dark punctuation marks of the cosmos, full stops in the sentences of stars, but even a full stop can be followed by another thought. So we continue. We listen to the ripples in space-time. We study the shadows of invisible giants. We follow the radiation, trace the entropy, map the geometry of nothingness. And through it all, we ask, what is this universe made of, and what is our place within it? Black holes may never give us all the answers, but in their silence, they invite us to ask better questions, and that, perhaps, is the greatest gift the darkness can offer.
What if we could look back in time? Not just decades or centuries, but billions of years. What if we could see the first stars ignite, the first galaxies swirl into form, the first light pierce through the primeval dark? What would we find in the universe's ancient dawn? Would it confirm everything we believe we know, or force us to rewrite the very laws of cosmic evolution? High above Earth, beyond the blue sky and above the clouds, a machine was sent on this very quest. A journey not of distance, but of time. It began its ascent silently rising through the thick atmosphere into the boundless night, bound for a destination unlike any other, 15 million kilometers from Earth, at a place where the gravity of the Sun and Earth perfectly cancel out. It came to rest, suspended in celestial equilibrium at the second Lagrange point. This was no ordinary observatory. It was a gateway to the deep past. There, in the cold vacuum of space, the James Webb Space Telescope slowly unfolded, like an origami flower blooming in zero gravity. Golden hexagonal mirrors clicked into alignment. Delicate sunshields stretched out like wings to block the harsh solar glare. And the observatory cooled, waiting, listening, watching. After decades of design and $10 billion of international collaboration, it was time a signal from Earth awakened the telescope's instruments, and at last, after years of anticipation, Webb opened its golden eye and began to see. What it saw changed everything. JWST, with its infrared gaze, was built to do many things: peer into stellar nurseries, study alien worlds for signs of life, and trace the faint afterglow of cosmic birth. But its most astonishing revelations came when it turned its attention to the very beginning, the first billion years after the Big Bang. Astronomers had long predicted what the early universe should look like, according to the Standard Model, our cherished lambda cold dark matter framework. The cosmos began small and simple. Galaxies were supposed to emerge slowly, assembling through countless mergers of smaller structures. They should have been faint, irregular, and primitive. But JWST revealed something startling. In the haze of ancient light, it found fully formed galaxies, large, luminous, structured, far too massive, far too early. They stood like ancient cities in the wilderness, monuments built in cosmic time, too short for such architecture. According to our best theories, they shouldn't even exist. For some, this was a call to update our models of star formation and early cosmic evolution. For others, it was far more unsettling, a crack, perhaps, in the foundations of modern cosmology. Could it be that dark matter behaves differently than we thought? Could dark energy, or even the fabric of space-time itself, be changing in ways we have yet to understand? This would not be the first time the universe has surprised us. From Galileo's first glimpse of Jupiter's moons to Hubble's discovery of an expanding universe, every new instrument has rewritten a chapter in our cosmic story. And now, with the James Webb Space Telescope casting its eye further into the past than anything before, we are once again at the threshold of discovery. So, what do these ancient galaxies truly tell us? Are they anomalies? Outliers to be explained? Or are they messengers from a deeper, more complex truth? This is the story of the universe's first great structures, the story of the galaxies that weren't supposed to be there, and the story of a telescope that may just change everything we thought we knew about the beginning of time. Eyes to the heavens. To gaze upward is to engage in an ancient ritual, a tradition as old as our own intellect. But the transformation of that gaze into a disciplined exploration began in earnest 4 centuries ago, when Galileo Galilei first pointed a telescope toward the night sky. Though the telescope had only recently been invented, primarily as a tool for earthly pursuits such as navigation and warfare, Galileo redirected its purpose toward the heavens. In doing so, he planted the seeds of a scientific revolution. With nothing more than a simple configuration of lenses, he observed the phases of Venus, the moons of Jupiter, and the pockmarked surface of the moon, shattering the long-held notion of celestial perfection. A few decades later, Isaac Newton took the next logical leap. By replacing lenses with a curved mirror, Newton eliminated the chromatic aberrations that plagued refracting telescopes and created the prototype for the modern reflector, laying the foundation for today's colossal observatories, including the James Webb Space Telescope. Newton's mechanical insights into optics may not have directly transformed astronomy, but his universal laws of motion and gravitation reshaped our understanding of celestial mechanics. The orbits of planets, moons, and comets were no longer seen as divine choreography, but as the natural consequence of mathematical laws, elegant, immutable, and pervasive. As telescope technology improved, so too did our ability to collect and refine the light of the cosmos. With each refinement, longer focal lengths, larger apertures, better mirror coatings, the universe revealed more of its grandeur, more of its complexity. By the mid-18th century, French astronomer Charles Messier was among those using telescopes to hunt for comets drawn to their glowing comas produced by the sublimation of ice and dust as they neared the sun. But Messier's work was repeatedly interrupted by fuzzy, unmoving smudges in the sky that did not behave like comets at all. These interlopers didn't move night to night. They refused to perform as expected. To avoid wasting time, Messier began cataloging them, curating a list of distractions, most of which turned out to be nebulae or star clusters within our own galaxy. Yet, unbeknownst to Messier, some of these faint objects were far more distant, entire galaxies in their own right. Through the 19th century, telescopic enhancements revealed structure in some of these enigmatic smudges, spiraling arm symmetry rotation, suggesting they were more than gas clouds. These visual cues led to a growing debate: were these spiral nebulae part of our own Milky Way? Or were they island universes, external galaxies far beyond our stellar neighborhood? This central question culminated in the Great Debate of 1920 between Harlow Shapley, who believed the Milky Way was the entire universe, and Heber Curtis, who argued for a far more expansive cosmos populated by myriad galaxies. It was Edwin Hubble who ultimately settled the matter, using the 25-meter Hooker telescope at Mount Wilson Observatory. Hubble resolved individual stars in the Andromeda Nebula and determined its distance via Cepheid variable stars. The results were staggering. Andromeda lay well beyond the Milky Way. Not only was our galaxy not alone, but the universe was vastly larger than previously imagined. And more still, Hubble discovered that nearly all galaxies are receding from us, their light stretched into longer, redder wavelengths by cosmic expansion. In a few short years, the universe had gone from a static stage to a dynamic, evolving entity, a cosmos that was born in a fiery beginning we now call the Big Bang. This monumental realization sparked new questions. If the early universe was hot, dense, and nearly uniform, where did the vast structures we see today originate? What mechanisms sculpted galaxies from that primordial smoothness? As telescopes continued to grow throughout the 20th century, both in aperture and technological sophistication, astronomers pursued these questions deeper into the dark. Earth-based observatories pushed the envelope with mirror diameters reaching 10 meters, allowing them to pierce through layers of dust and reach fainter, more distant light. But they were ultimately limited by Earth's own atmosphere, whose constant turbulence blurred incoming starlight. The solution was to escape the atmosphere entirely. In 1990, the Hubble Space Telescope was launched into low Earth orbit, carrying a modest 25-meter mirror but free from atmospheric distortion. The clarity of its images transformed both science and public imagination, producing iconic photographs of galaxies, nebulae, and deep cosmic vistas that adorned both academic journals and classroom posters around the world. But science does not rest on its achievements. Even before Hubble had reached full operation, plans were underway for its successor. A telescope that would peer not merely into distant galaxies but into cosmic history itself. The James Webb Space Telescope. A marvel of modern engineering was envisioned to carry a 65-meter segmented mirror, far too large to fit into a rocket in one piece. Like some vast piece of origami, the telescope would have to be folded for launch and delicately unfurled in space. Its destination was not Earth orbit, but a gravitational perch, 15 million kilometers away the Sun, Earth Lagrange point L2. There, in the frigid silence of deep space, it would be shielded from the Sun's heat by a 5-layer sunshield the size of a tennis court, cooled until it could detect the faint infrared glow of the earliest galaxies. After decades of delays, cost overruns, and technological challenges, JWST launched on Christmas Day 2021, riding atop an Ariane 5 rocket and carrying with it the hopes of an entire generation of astronomers. Its mission to chart the life cycles of stars, to study the atmospheres of distant exoplanets for signs of life, and most ambitiously to search for the first galaxies ever formed to witness the dawn of structure in the universe. What it would find no one could say for sure, but one question loomed large. Where did galaxies come from, and when did they arise in the cosmic timeline? The answer lay in light that had traveled for over 13 billion years, emitted by stars and galaxies that lived and died long before Earth even formed. As James Webb opened its golden eye to the deep sky, it began collecting this ancient light, offering us not just a glimpse, but a new window into the formative epochs of the cosmos, one capable of changing everything we thought we knew. The first galaxies. To understand the first galaxies, we must embark on a journey not merely through space, but through time, reaching back across the eons to a cosmos still unformed, still raw with potential. The tale of these primordial structures begins with a paradoxical fusion, a story that connects the largest scales of the universe to its smallest weaving together, the tapestry of galaxies from quantum ripples in space-time itself. Our modern tools for exploring this tale are many, but one of the most transformative is the Planck satellite launched in 2009, and for a time, the coldest known object in space. Its mission was not to observe stars nor even galaxies. Instead, Planck mapped the entire sky in exquisite detail, focusing on the cosmic microwave background, the afterglow of the Big Bang. This radiation is ancient, stretching across the universe at a uniform temperature of roughly 273 degrees above absolute zero. But within that uniformity lies the key to cosmic structure: tiny temperature fluctuations, 1 part in 100,000, representing the earliest imprints of gravitational variation. These ripples were not random. They originated from quantum fluctuations during an extraordinary event known as cosmic inflation, which occurred just a fraction of a second after the Big Bang. Inflation magnified microscopic fluctuations to macroscopic scales, imprinting space itself with density variations. When inflation ended, these frozen quantum disturbances were filled with energy, becoming the seeds of galaxies yet to form. As the universe cooled, particles condensed. Within the first microsecond, quarks were locked into protons and neutrons. After a few minutes, these fused into the first atomic nuclei, mostly hydrogen and helium. The fires of primordial nucleosynthesis burned briefly but profoundly, leaving behind a smooth sea of atomic matter, now expanding and cooling through time. Yet for nearly 100 million years, the cosmos lay in darkness, a period aptly named the Cosmic Dark Ages. Though matter existed, no stars had yet formed to light the skies. Still, gravity worked silently, shaping structure through the invisible scaffolding of dark matter. Unlike ordinary matter, dark matter does not interact via light, but its gravitational pull is immense. It began to collapse into overdensities, regions where matter was slightly denser than average. These overdensities grew and merged, forming the first dark matter halos, gravitational wells into which ordinary matter would later fall. Ordinary matter hydrogen and helium gas responded differently. It could cool, compress, and radiate energy, unlike its dark counterpart. Eventually, as gas settled into these halos, it began to fragment. The densest fragments collapsed under their own weight, and in their cores temperatures rose high enough for nuclear fusion to ignite. Thus, after a cosmic slumber, the first stars flared into being. These stars, known as population 3 stars, were fundamentally different from the stars of today. They contained only hydrogen and helium, lacking the heavier elements, what astronomers call metals, that are forged in stellar interiors. Without these metals to aid cooling, these early stars grew to tremendous sizes, often exceeding 100 times the mass of our Sun. They burned hot and bright, emitting intense ultraviolet radiation, but their lives were brief, just a few million years before ending in dramatic supernova explosions or collapsing directly into black holes. With the birth of these first stars came the epoch of reionization. Their powerful radiation ionized the surrounding neutral hydrogen, stripping electrons from atoms and transforming the universe's dark plasma into a transparent, glowing cosmos. This transition, marked by growing bubbles of ionized gas, signaled a universe awakening. Yet the story of the first galaxies had only just begun. Stars do not form in isolation. They cluster their gravitational attraction, drawing them into associations. The early universe seeded with these dark matter halos, and increasingly enriched with metals from supernovae, began to assemble the first proto-galaxies. But defining a first galaxy is not straightforward. Unlike stars, which ignite in a discrete event, galaxies evolve gradually. They grow through accretion, the slow gathering of gas, and through mergers where smaller systems collide and combine into larger ones. What we observe today as majestic spirals and giant ellipticals began as modest knots of matter coalescing under the persistent influence of gravity. These formative galaxies were not all successful. In the smallest halos, a single population 3 star could disrupt the entire system. Its supernova might expel all remaining gas, halting further star formation, and leaving behind a dark halo, what we call a dark galaxy. Such ghostly remnants may still drift unnoticed through the cosmos. However, in larger halos, gravity prevailed, gas was reaccreted, and successive generations of stars began to form. These newer stars, now enriched with trace amounts of carbon, oxygen, and heavier elements, were markedly different from their predecessors. The presence of metals altered the opacity of stellar material, affecting how energy moved through the star and changing its evolution. Stars, like our Sun, with lifespans of billions of years, became possible. Thus began the transition from the first galaxies to the galactic zoo we observe today. The most massive halos continued to grow, attracting and merging with others. This hierarchical buildup is a cornerstone of the LCDM model, our best current theory for the structure of the universe. But not all galaxies grew at the same rate. Some remained small, fragile collections of stars, while others ballooned into giants. As mass increased, so did stability. Larger galaxies retained their gas even after supernova, supporting sustained star formation across cosmic time. These galaxies became cosmic engines, generating light metals and structure on ever larger scales. Meanwhile, as stars aged and died, the heavy elements they produced were dispersed, enriching the interstellar medium. This chemical evolution is crucial. Without carbon and oxygen, there would be no Earth, no life, and no astronomers to tell this story. What began as imperceptible quantum ripples now echoed across billions of light years. The cosmic microwave background, once uniform, had evolved into a universe populated with galaxies. each a complex ecosystem of gas stars, black holes, and dark matter. And though we can simulate much of this history with remarkable precision, observations always bring surprises. The James Webb Space Telescope, our most powerful observatory to date, has begun to peer into this epoch. Already, it has challenged expectations, revealing galaxies more massive, more structured, and more numerous in the first billion years than theory had predicted. These findings do not undermine our cosmological framework, but instead sharpen it. As in all science, anomalies are invitations, prompts to revisit assumptions, refine models, and look deeper. The early universe is a frontier not only of time and distance, but of knowledge. We stand now at its edge, our instruments pointed skyward, seeking in the ancient light the answers to questions formed by the fusion of curiosity and reason. The first galaxies were not monumental in size nor grand in appearance, but they were monuments of process evidence that gravity, chemistry, and time, guided by the laws of physics, could sculpt the void into luminous form. From the tiny ripples imprinted in the quantum fog of the early universe to the brilliant spirals now wheeling across our skies. This is the journey of structure, of complexity, and ultimately of us. For somewhere in one of those fledgling galaxies, a sun would one day rise, and orbiting that sun, a small rocky world would look back at the stars and wonder how it all began. The Galactic Zoo. In 1932, amidst the dawn of global radio communications, a peculiar discovery emerged not from the optical lens of a telescope, but from the static of a radio receiver. Carl Jansky, an engineer at Bell Telephone Laboratories, was investigating sources of interference in transatlantic radio signals when he noticed something strange, a persistent hiss of background noise, faint but measurable. Initially, he attributed it to terrestrial causes, perhaps lightning or electrical equipment. But the mystery deepened when Jansky observed that this static did not align with the rhythm of Earth's 24-hour solar day. Instead, it shifted ever so slightly, adhering to a cycle just under 24 hours. Sidereal time, the time taken for distant stars to return to the same position in the sky. This seemingly minor discrepancy of 4 minutes per day carried profound implications. It meant that the source of this radio interference was not of earthly origin, nor even tied to the sun, but came from well beyond our solar system. Jansky had inadvertently detected radio waves from the Milky Way itself, the first ever confirmed reception of electromagnetic radiation from deep space outside the visible spectrum. This serendipitous moment marked the birth of radio astronomy. Although Jansky himself was redirected to other duties and did not pursue the discovery further, his name became immortalized in the field. Today, we measure the strength of radio emissions from celestial sources in Jansky's. Others picked up the mantle. Notably, Grote Reber, a young engineer and amateur radio enthusiast, constructed the world's first purpose-built radio telescope in his backyard. For a time, he was the only practicing radio astronomer on Earth. Through his work, Reber confirmed Jansky's findings and revealed that the Milky Way emitted radio waves across the sky, opening a new window onto the cosmos. Soon as radio telescopes proliferated and improved, astronomers discovered more than just emissions from our own galaxy. They detected incredibly powerful radio sources, compact, bright, and seemingly point-like, that emitted energy on a scale difficult to reconcile with known stellar processes. These mysterious objects came to be known as quasi-stellar radio sources, or quasars. Appearing star-like in optical images but blazing with radio energy, quasars were later understood to be powered by supermassive black holes, some with masses exceeding 1 billion suns, feeding on surrounding matter and releasing enormous amounts of energy as they accreted gas and dust. These beacons could be seen across billions of light years, revealing not only their own immense power, but also illuminating the early universe itself. Quasars represented just one expression of the intense activity that characterized the first few billion years of cosmic history. During this primordial epoch, the universe blazed with light and change. First stars ignited, first galaxies assembled, and first black holes fed ravenously. But as the universe aged, the youthful fervor of cosmic activity waned. Star formation began to slow, and galaxies matured into more stable configurations. Yet even in this apparent calm, gravity continued its work, relentlessly driving evolution on every scale. Galaxies, like living organisms, changed with time. Small galaxies merged and coalesced into larger ones. Larger galaxies in turn consumed their surroundings and grew more massive still. Some galaxies developed distinct structures shaped by their internal dynamics. Disk-shaped galaxies like our Milky Way spun into elegant spirals, their rotation sustained by the conservation of angular momentum. Cold gas within these spinning disks collapsed into stars, forming the grand design spirals that populate astronomical catalogs today. Other galaxies suffered more turbulent fates. Violent mergers between massive galaxies often disrupted their ordered rotation, transforming them into chaotic amorphous systems known as elliptical galaxies. Lacking the structured spiral arms of their cousins, these spheroidal galaxies contain older stellar populations and less gas, signaling the end of vigorous star formation. The cosmos thus revealed a dichotomy in galactic morphology: spirals and ellipticals, each reflecting distinct evolutionary pathways shaped by collisions and environmental interactions. Yet not all galaxies fit these tidy classifications. Some appear misshapen or irregular, likely distorted by gravitational interactions, past mergers, or ongoing encounters with neighboring systems. These irregular galaxies serve as transitional objects, snapshots of galaxies caught mid-transformation, still bearing the scars of their recent histories. In the observable universe, astronomers estimate the existence of up to 1 trillion galaxies, varying wildly in scale. Most are modest, containing a few billion stars, but a select few are true giants, hosting hundreds of billions or even trillions of stars. These galaxies are not scattered randomly. Rather, they trace a vast interconnected structure of matter known as the cosmic web, a lattice of filaments and nodes shaped by the primordial fluctuations seeded during inflation and sculpted by dark matter over cosmic time. In this web, vast voids regions nearly devoid of galaxies span millions of light years, while matter flows along filaments and sheets toward gravitational wells. These wells correspond to massive conglomerates of galaxies and dark matter. Galaxy clusters. Clusters are gravitational fortresses housing hundreds or thousands of galaxies swimming in a hot plasma called the intracluster medium, all immersed in massive dark matter halos. At the heart of the largest clusters reside the titans of the galactic realm, CD galaxies, monstrous ellipticals that dominate their environment and continue to grow through cannibalism and accretion. Clusters themselves form larger structures, superclusters which span hundreds of millions of light years. Our own Milky Way is part of one such structure, the Laniakea supercluster, encompassing millions of galaxies. Whether superclusters are gravitationally bound or merely transient associations remains an open question, but they mark the largest coherent features in the known universe. Not all galaxies live in clusters. In fact, most reside in smaller associations known as galaxy groups. These more intimate gatherings consist of a few to several dozen galaxies, typically anchored by 1 or 2 massive members. Our Milky Way is part of such a group. The local group, which includes the Andromeda Galaxy, the Triangulum Galaxy, and over 100 dwarf galaxies. Many of these faint companions have only recently been discovered through deep sky surveys enabled by modern telescopes. The local group, while unassuming compared to massive clusters, has become a laboratory for understanding galactic evolution. In particular, it has revealed a truth that reshapes our conception of galaxies as static finished entities. Galaxy evolution is not over. In fact, it is happening around us right now. A striking example of this ongoing process was discovered in the early 1990s by Rodrigo Ibada, a young graduate student at the University of Cambridge, working with the Anglo-Australian Telescope in New South Wales. Ibada was studying the dynamics of stars near the Milky Way's central bulge. His observations, conducted with the aid of optical fiber instruments capable of measuring the motion of dozens of stars, simultaneously uncovered something strange. Amid the random motions expected in the galactic bulge, a subset of stars appeared to be moving coherently, as if they shared a common origin. Ibata ruled out measurement errors and computational mistakes. The evidence grew harder to ignore. With the guidance of his supervisors, Jerry Gilmore and Mike Irwin, Ibata reached a bold conclusion. These stars were not native to the Milky Way. They belonged to a separate external system, an intruding dwarf galaxy. The discovery of the Sagittarius dwarf galaxy provided direct evidence that the Milky Way was in the process of consuming another galaxy. This satellite galaxy, stretched and distorted by our galaxy's gravity, was being torn apart, its stars scattered into tidal streams across the sky. What was once a coherent stellar system would eventually be subsumed into the Milky Way's halo, lost among its billions of stars. Since then, astronomers have found that Sagittarius is not alone. The Milky Way is consuming multiple dwarf galaxies, remnants of which are still detectable in the form of faint stellar streams. Andromeda, our galactic neighbor, is doing the same. Galactic cannibalism is not an occasional event. It is a central mechanism of galactic growth. The peaceful serenity we attribute to our night sky belies a violent and ongoing process of accretion and destruction. Thus, our understanding of the galactic zoo, the diversity of galaxies and their behaviors, has matured through decades of observation and theoretical work. We now comprehend galaxies not as isolated objects, but as products of environment history and ongoing interaction. They are born in the dense knots of dark matter, nurtured by gravity and gas, shaped by internal dynamics and transformed by cosmic encounters. They live, grow, and sometimes die, collapsing into black holes or being devoured by larger systems. Yet for all our knowledge, the universe continues to challenge us. As recently as 2022, new observations from the James Webb Space Telescope hinted that the earliest galaxies might be more massive and more developed than current models predict, stirring debates and forcing us to re-examine long-held assumptions. From the quantum ripples that ceded structure to the majestic spirals and monstrous clusters we observe today, the cosmos reveals itself as both an archive of ancient processes and an active dynamic entity. To map this evolution is to trace a vast and interwoven story, a narrative written in stars and dark matter and gas and radiation in the grand interplay of gravity and time. It is the story of everything we see in the night sky, and it is still being written. The James Webb Mystery. It began with a roar that echoed across the blue Christmas morning sky, a column of fire lifting humankind's most ambitious eye into the heavens. A telescope unlike any before. It folded like cosmic origami, was flung across the void to take position 1.5 million kilometers from Earth, far beyond the pull of our planet's gravity, to a place where the forces of Earth and Sun are balanced in celestial harmony. There, at the second Lagrange point, JWST unfurled its golden mirrors, cooled to the chill of deep space, and prepared to look far back toward the first flickers of starlight that ever pierced the darkness. As the James Webb Space Telescope opened its eye on the young universe, astronomers around the globe found themselves transfixed and then puzzled. What they saw in those first images from the primordial cosmos did not align with what decades of theory had led them to expect. There, shining from a time less than 1 billion years after the Big Bang, were galaxies that looked too big, too luminous, too structured. Some were beautiful, rotating disks, grand spirals eerily reminiscent of our own Milky Way. But how could this be? In a universe still in its infancy, how had such galaxies already matured? One paper, cheekily titled "Panic at the Disks," captured the sentiment cosmologists watched as headlines around the world began to declare an existential crisis had JWST disproven the very foundations of cosmology. Was the Big Bang model broken? Were the equations of the universe undone? To make sense of the excitement and the unease, we must journey into the very heart of modern cosmology and ask a simple but profound question: what kind of universe do we live in? The story begins, as so many great stories do, in the early 20th century. Albert Einstein, forging a new understanding of gravity, had just unveiled his general theory of relativity, a framework in which space and time were no longer passive stages, but active participants in the cosmic dance. Others followed in Einstein's wake: Friedman, Lemaitre, Robertson, Walker. Their solutions to Einstein's equations revealed a startling possibility: space itself was not static. The universe could stretch, evolve, and expand. And then came Edwin Hubble. In the 1920s, observing from Mount Wilson, he found that distant galaxies were redshifted. That is, their light was stretched as if fleeing from us. The more distant the galaxy, the greater the shift. The conclusion was inescapable. The universe was expanding. And if it was expanding now, it must have been smaller, denser, and hotter in the past. Thus was born the Big Bang theory, not an explosion in space, but an expansion of space itself from a seething, high-energy beginning. But relativity, elegant as it is, offers not one solution, but many. Mathematically, the equations can describe countless possible universes. To know which one we inhabit, astronomers needed data, specifically two crucial measurements: the current rate of expansion and the contents of the universe. The first of these is the Hubble constant, which tells us how fast galaxies recede as a function of their distance. The second concerns the energy budget of the cosmos, how much of it is made of matter, radiation, and other more exotic components. Measuring these values became the central task of observational cosmology for most of the 20th century. Determining the Hubble constant was notoriously difficult. The universe, unfortunately, does not provide measuring sticks. Estimating cosmic distances required creative methods using standard candles like Cepheid variables and Type Ia supernovae, whose intrinsic brightness is known to deduce their distance from apparent brightness. For decades, astronomers debated whether the Hubble constant was closer to 50 or 100 kilometers per second per megaparsec, a disagreement that translated into wildly different estimates of the universe's age. It was only in the 1990s, with the deployment of the Hubble Space Telescope, that clarity began to emerge. With unprecedented precision, HST measured the distance to nearby galaxies, settling on a value near 72 kilometers per second per megaparsec, implying a universe roughly 138 billion years old. Visible matter stars, planets' gas was easy enough to tally, but something strange lurked in the motions of galaxies and clusters. Spiral galaxies rotated too fast at their edges. Clusters of galaxies held together despite insufficient visible mass. The only explanation was that some unseen substance, dark matter, was exerting gravitational influence. Though invisible to light, its presence was undeniable. The universe, it seemed, was mostly made of things we could not see. And then came a revelation so startling, it won the Nobel Prize 2 teams. The Supernova Cosmology Project and the Higgs Supernova Search Team studied the light of exploding stars to chart the expansion history of the universe. Their expectation was clear. Gravity, acting over time, should slow the expansion. But the data told a different story. Instead of decelerating, the universe was accelerating, expanding faster and faster as time went on. What could be driving this cosmic acceleration? The answer, though speculative, lay in the mathematics of general relativity, a mysterious form of energy permeating all of space, exerting a repulsive pressure. It became known as dark energy, a force unlike any seen before, whose nature remains one of the deepest mysteries in physics. With these discoveries, cosmologists assembled a model of the universe now known as LCDM, lambda, cold, dark matter. Lambda stands for the cosmological constant, Einstein's term for dark energy. CDM refers to cold dark matter, slow-moving and clumping, which seeds the formation of galaxies. According to LCDM, the universe is 138 billion years old, composed of about 5% ordinary matter, 27% dark matter, and 68% dark energy. This model has passed countless observational tests. It predicts the pattern of cosmic microwave background radiation, the distribution of galaxies on large scales, and the evolution of cosmic structure. It is by all accounts an astounding triumph of science. The galaxies observed by JWST appeared not only earlier than expected, but brighter, more massive, and more structured than models had predicted. Some appeared to contain hundreds of billions of stars, less than a billion years after the Big Bang. In theory, such massive systems shouldn't have had enough time to form. Cosmological models like LCDM govern the evolution of the universe on the largest scales, how space expands, how matter clumps. But to predict the formation of galaxies, we must go further. We must simulate the flows of dark matter and gas, the cooling of plasma, the birth of stars, the feedback of supernovae and the ravenous hunger of black holes. This is astrophysics in full complexity, a dance of scales and forces that challenge even our most powerful computers. To cope, astronomers employ recipes, simplified rules embedded in simulations to approximate the messy physics of galaxy formation. These recipes are based on the best available data but often rely on assumptions. One of the most critical is the stellar initial mass function, a statistical description of the distribution of star masses formed in a given gas cloud. In the local universe, the IMF is relatively well constrained. But what if it was different in the early cosmos? If, for example, early star formation favored more massive luminous stars, then young galaxies would shine more brightly than expected, for their mass astronomers, assuming a local IMF, would overestimate their size and maturity. Such a skewed IMF could help explain why JWST's galaxies seemed anomalously bright. Perhaps they weren't so massive after all, just composed of hotter, more massive stars. Moreover, early results from JWST were based on rapid preliminary analyses. The telescope's instruments are extraordinarily sensitive, and interpreting their data requires meticulous calibration. Redshifts must be confirmed spectroscopically, not just estimated photometrically. Initial excitement often gives way to more sober reanalysis. And that is precisely what is happening. As JWST continues its observations and astronomers refine their models, the panic is subsiding. The LCDM framework remains intact. The early universe may be more complicated than expected, richer, more dynamic, but that is not a crisis. It is the fulfillment of JWST's mission. For telescopes do not exist to confirm what we already know. They are built to challenge our assumptions, to expand the boundaries of the known. Every deviation, every outlier, every unexpected galaxy is a clue, an invitation to look again, think deeper, and refine our understanding of the cosmos. What the James Webb Space Telescope is revealing is not the failure of cosmology, but its vitality. It reminds us that science is not a monument, but a process, a conversation with nature that unfolds over time. It is a testament to our curiosity, our creativity, and our willingness to question even our most cherished theories. In the end, the galaxies JWST glimpsed in the early cosmos are not harbingers of doom, but messengers of wonder. They whisper of a universe that came alive faster than we imagined, of stars that blazed into existence amid chaos, and of a cosmos still full of secrets waiting to be unveiled. And so the story continues, one observation at a time, one photon at a time, as we reach deeper into the darkness, searching not for certainty, but for understanding.
What was there before time? If space had a beginning, what was it born from? Can something truly arise from nothing? And if the universe had a first moment, what caused it? Or was it always there? In a fraction of a second, from a point smaller than a subatomic particle, everything, space, time, matter, energy, came into being. One moment there was nothing. The next, there was a universe. Ours. This is not merely a tale of stars and galaxies. It is the greatest mystery science has ever known. How can there be a beginning to everything? And what, if anything, came before it? Everything we understand about our cosmos is rooted in causality, the idea that events unfold because something causes them to happen. From the fusion inside stars to the orbit of planets, we look for processes, for mechanisms, for reasons. But when it comes to the origin of the universe itself, those rules seem to falter. Some physicists, like the late Stephen Hawking, proposed a radical answer. Perhaps there was no before. If space and time are part of the universe, then the beginning of the universe was also the beginning of time. Before that, the concept of before becomes meaningless, like asking what lies north of the North Pole. Or perhaps the Big Bang wasn't the ultimate beginning, but rather the boundary of what we can currently observe. According to the theory of cosmic inflation, our universe experienced a rapid and incomprehensible expansion in its earliest moments, a burst that shaped the structure of all we see. But inflation may not have ended everywhere. Some theories suggest it continues eternally, spawning countless other bubble universes in an endless multiverse. Other scientists imagine something even more cyclical. In the Big Bounce model, our universe is just the latest in a series, expanding, contracting, and rebirthing itself across infinite cosmic epochs. Still others look deeper into the fabric of spacetime. Roger Penrose proposes that at the extremes, when the universe is unimaginably vast, or infinitesimally small, time and scale may lose meaning altogether, rendering the birth and death of universes indistinguishable. And beyond that, the mathematical symphony of superstring theory hints that our universe may be just one membrane, or brain, floating in a higher dimensional reality, its creation the result of a collision between dimensions. Each of these ideas offers a different chapter in the story of creation, but none yet offer the final word. So while the origin of our universe remains unsolved, what we know is this: something did happen. 13.8 billion years ago, our universe began. And in seeking to understand it, we are not only searching for the start of space and time, we are also searching for the boundaries of human understanding. The Planck era, the first pulse of cosmic existence. In the pursuit of understanding the origins of our universe, there exists a boundary, an event horizon of knowledge, beyond which lies not darkness, but rather a blinding intensity of energy and uncertainty. This is the Planck era, the first infinitesimal moment after the universe began, a period so brief, so dense, and so energetic that our deepest theories of physics collapse into paradox and mathematical singularity. To traverse the conceptual terrain of the Planck era is to abandon the world as we know it. The constants of nature, distance, time, temperature, mass, all assume values that defy intuitive comprehension. But it is precisely by grappling with these extremes that we approach the roots of reality itself. At first glance, one might imagine the hottest locales in the cosmos to be found within stars. These massive thermonuclear reactors shine through the centuries, powered by the relentless fusion of atomic nuclei at their cores. Temperatures at the heart of our sun, for instance, reach a blistering 15 million degrees Celsius. A journey into such a stellar furnace would obliterate any conventional matter long before reaching the center. Yet even this infernal heat is moderate by cosmic standards. Supernovae, the violent deaths of massive stars, mark a dramatic escalation in thermal energy. In the explosive collapse and rebound of a dying star's core, temperatures can soar to over 100 billion degrees Celsius. This heat is sufficient to forge elements heavier than iron, seeding the universe with the ingredients for life itself. Yet still, this is not the summit of temperature. That distinction belongs, astonishingly, not to the farthest reaches of space, but to a laboratory on Earth. In 2012, deep beneath the Alps near the Swiss-French border, the Large Hadron Collider at CERN achieved a temperature of roughly 5.5 trillion degrees Celsius. This was the result of smashing lead ions together at near-light speeds, creating a microscopic fireball of quark-gluon plasma, primordial state of matter believed to have existed shortly after the birth of the universe. In that fleeting instant, the LHC replicated conditions not seen in 13.8 billion years. And yet, as titanic as that figure may seem, it is only a fragment of the full picture. The maximum temperature that the universe can theoretically support is far beyond what our particle accelerators can touch. This upper bound is known as the Planck temperature, the highest meaningful temperature in physical theory. Beyond this point, temperature ceases to be a useful concept, because the energies involved would tear apart the very particles that constitute reality. Temperature, in the language of physics, is not merely a measure of heat. It is the average kinetic energy of particles, their motion, vibration, and agitation. At absolute zero, all motion theoretically ceases. At the opposite extreme lies the Planck temperature, a figure so immense that it marks the limit beyond which matter and energy can no longer coexist in known forms. It arises from a confluence of constants, the speed of light, the gravitational constant, and Planck's constant, a trio of quantities that together define the Planck units. These natural units set the scale at which quantum mechanics and gravity converge into a single inseparable phenomenon. Max Planck, the pioneering German physicist whose name graces these concepts, introduced the idea of quantized energy at the dawn of the 20th century. His work laid the foundation for quantum theory, beginning with the revolutionary insight that light is not a continuous wave, but is emitted in discrete packets, photons. From this initial quantization of electromagnetic radiation, a new vision of nature emerged, one in which even space, time, and gravity might be subject to quantum rules. From Planck's work arises a set of fundamental units that define the limits of measurable reality. The Planck length, for instance, is the smallest meaningful unit of space, approximately 100 quintillion times smaller than a proton. It is the length scale at which classical ideas of geometry and distance begin to dissolve under the influence of quantum fluctuations. The Planck time, the time it takes for light to traverse a single Planck length, is even more incomprehensible, a fleeting instant, so brief that it makes nanoseconds appear eternal by comparison. This is the age of the universe at the onset of the Planck era, a time when our observable cosmos was only 1 Planck time old and had a diameter of just 1 Planck length. And then there is the Planck temperature. This is not merely the hottest anything can be, it is the point at which traditional physics ceases to be reliable. At this temperature, the energy contained within a single region of space is so concentrated that it distorts spacetime itself. Quantum uncertainty and gravitational collapse occur simultaneously, and the very concept of particles breaks down. To understand the relevance of Planck units, one must consider the nature of cosmic expansion. The universe, as we now understand it, has been expanding and cooling since its inception. Whether or not the universe is spatially infinite, it is clear that our observable region, the portion from which light has had time to reach us, is finite, bounded by the age of the cosmos and the speed of light. As we look back in time, the observable universe contracts. Its mass-energy content remains the same, but its volume diminishes. Eventually, we reach the Planck time, the earliest definable moment in cosmic history. At this point, the density and temperature of the universe reach their maximum possible values. The entire observable cosmos, now trillions of times smaller than a proton, is compressed into a fireball of unimaginable energy. This is the Planck era. In today's cosmos, the behavior of matter and energy is governed by 4 fundamental interactions: the strong nuclear force, the weak nuclear force, electromagnetism, and gravity. Each of these forces has a corresponding messenger particle: gluons for the strong force, W and Z bosons for the weak force, photons for electromagnetism, and a hypothetical graviton for gravity. By the end of the 19th century, Planck and others had already begun to see that electromagnetism could be described in terms of quantized fields. Later, it became clear that the strong and weak forces were also susceptible to quantum treatment. Gravity, however, remained the outlier. Einstein's general theory of relativity redefined gravity not as a force, but as the curvature of spacetime caused by mass and energy. This model has withstood a century of experimental verification, from the bending of starlight to the detection of gravitational waves. But it breaks down at quantum scales. During the Planck era, the entire observable universe existed within a volume so minuscule that quantum effects could not be ignored. Gravity, operating on this scale, must itself be quantized. But our current theories cannot describe such a scenario. Herein lies one of the most profound challenges in modern physics: the incompatibility between general relativity and quantum mechanics. Each is supremely successful within its own domain. General relativity governs the large-scale structure of the universe, while quantum mechanics governs the subatomic realm. But at the Planck scale, the two must coexist, and yet their mathematical frameworks conflict. This impasse has spurred the search for a unifying theory: quantum gravity. Such a theory would describe the behavior of gravity in quantum terms, reconciling the smooth geometry of Einstein with the probabilistic fuzziness of quantum physics. Various candidates have emerged. One is the graviton, a hypothetical particle that transmits the gravitational interaction. However, gravity is vastly weaker than the other forces, and detecting a single graviton remains beyond our experimental reach. Other approaches take radically different forms. loop quantum gravity suggests that space-time itself is not continuous, but composed of discrete loops of quantum geometry. Space becomes quantized, structured, like a woven fabric of microscopic threads. This theory reformulates general relativity in terms of these loops, offering new mathematical tools for addressing gravity on small scales. Perhaps the most ambitious proposal is string theory. String theory also gives rise to M-theory, an overarching framework that includes not just strings, but also higher dimensional objects known as branes. These entities may stretch across multiple dimensions, and their interactions could give rise to entire universes. Even in the absence of experimental data, theoretical physicists have attempted to visualize the texture of space-time at the Planck scale. In the 1950s, the American physicist John Archibald Wheeler introduced the concept of quantum foam, a seething, dynamic structure underlying the fabric of space-time. According to Wheeler, the uncertainty principle renders space and time fundamentally unstable at the smallest scales. Instead of smooth continuity, the Planck-era universe resembles a chaotic froth. Tiny wormholes and micro-black holes flicker into and out of existence, governed by fluctuations that defy classical causality. The orderly space-time we experience today emerges from this quantum chaos only as the universe expands and cools. In such a regime, it becomes impossible to measure position, energy, or time with precision. The very concepts we use to describe physical phenomena lose their coherence. And yet, out of this uncertainty, order will eventually emerge. The Planck era does not last. It is over almost as soon as it begins, 100 million trillion trillionths of a second after the Big Bang. Yet, in that ephemeral flicker, the stage is set for everything that follows. As the universe expands, it cools ever so slightly. The quantum fluctuations begin to stabilize. The fundamental forces differentiate from one another. The first particles condense from energy. This marks the end of the Planck era and the beginning of a universe that, while still unrecognizably alien by modern standards, can be described by the laws of physics we know today. From this moment forward, we can trace the universe's evolution with increasing clarity through the formation of atoms, stars, galaxies, and eventually, life. But the mystery of that first moment remains. It is the question at the heart of cosmology, quantum physics, and gravitation alike. What happens when all the forces of nature become one? The answer remains hidden, encrypted within the mathematics of theories yet to be proven, and perhaps forever beyond the reach of experimentation. Still, to gaze backward into that initial moment is not futile. It is an act of intellectual courage, a tribute to the human spirit's unyielding drive to understand. In contemplating the Planck era, we confront not only the limits of our knowledge, but the birth of reality itself. Grand unification, the first flicker beyond the Planck curtain. In the modern cosmos, all matter and energy conform to the governance of four fundamental forces: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. These invisible agents dictate the behavior of everything from galaxies to atoms, from the orbit of Earth around the Sun to the biochemical flicker of neurons in a human brain. Yet these forces are not equals. Gravity, despite shaping the architecture of stars and planetary systems, is the weakest among them, so feeble, in fact, that a modest flex of the human arm can overcome Earth's gravitational pull. Contrast this with the strong nuclear force, an overwhelming adhesive that binds protons and neutrons within atomic nuclei and ensures the cohesion of matter itself. Electromagnetism is no less pivotal, enabling light, electricity, chemistry, and the very sensory interaction between our minds and the material world. The weak nuclear force, often overlooked due to its name, plays a vital role in radioactive decay and the nuclear reactions that power the stars. In our present epoch, these forces appear distinct, their identities well-defined, and their behaviors experimentally verified. But the early universe was a far more chaotic and exotic domain, a crucible in which the distinctions we now observe were blurred and the boundaries between forces collapsed. Immediately following the Planck era, during what is known as the Grand Unification Epoch, the cosmos operated under a dramatically reduced set of physical rules. The four fundamental forces were not yet separate. Instead, the universe was governed by only two: gravity and emerged force, uniting the strong, weak, and electromagnetic interactions. To comprehend how three distinct forces could dissolve into one, we must turn to the concept of energy unification. At high enough temperatures and densities, the familiar properties of these forces begin to shift. Analogously, consider a spinning coin in the air. Before it lands, the coin does not present a definite face. The distinction between heads and tails blurs into a whirling unity. Only once its kinetic energy dissipates does the coin settle, and the outcome becomes determined. This metaphor captures the spirit of unification at high energies. As we elevate the temperature, the electromagnetic and weak nuclear forces begin to merge, forming what physicists term the electroweak force. At even higher energy thresholds, far beyond what our current particle accelerators can achieve, the strong nuclear force is predicted to join this union. The result is a theoretical composite interaction known as the electrostrong force. The Grand Unification Epoch is defined by the reign of this unified interaction. Grand unification theories, as proposed within the framework of quantum field theory, strive to mathematically describe this convergence. Although the electroweak unification has been empirically verified through experiments at CERN and other particle colliders, the unification of the strong force remains speculative. The requisite energy scale, around 10 to the 16th GeV, is utterly beyond current human engineering. Not even the cataclysmic energies of supernovae or relativistic jets from black holes approach this threshold. Thus, the electrostrong interaction exists only in theory, a tantalizing glimpse at the possible symmetry of nature's foundation. During the fleeting instant of grand unification, beginning just after the Planck time, the universe was unimaginably hot and dense. Temperatures soared to 10 to the 32 Kelvin, and space-time itself was subject to quantum fluctuations. In this realm, particle identity was not fixed. Instead, the universe seethed with instability and transformation. Particles flickered into and out of existence, mediated by force carriers that themselves defied stable classification. Photons transmuted spontaneously into quark-antiquark pairs. Leptons decayed into hadrons. And all of this occurred in a bath of pure energy, constrained within a spatial volume smaller than a quark. In this bizarre arena, the electrostrong force operated through its hypothetical messengers, unified bosons capable of facilitating transitions not permitted by today's standard model. Quarks could become leptons, and antimatter could transform into matter, and vice versa. Conservation laws, as we understand them now, were not yet enshrined. The universe was fluid, its physical laws still in formation. Symmetry reigned, and identity was optional. But symmetry, as nature so often reveals, is fragile. Roughly 10 to the 36th seconds after the birth of time, a dramatic phase transition shattered this fleeting unity. As the universe expanded, it cooled. The energy density dropped below the unification threshold, and the strong nuclear force decoupled from the electrostrong amalgam. The once spinning coin began to settle. What was one became two, and from this point onward, the strong force operated independently. This symmetry breaking was no quiet affair. it released a tremendous amount of latent energy, seeding the universe with new particles and possibly fueling a period of exponential inflation, an astonishingly rapid expansion that smoothed out the early cosmos and set the stage for the emergence of large-scale structure. Whether this inflationary event coincided precisely with the end of the grand unification epoch remains a topic of theoretical debate, but many models suggest a close relationship. Importantly, this symmetry breaking also introduced a significant problem for physicists: the matter-antimatter asymmetry. Theoretically, the unified force should have produced equal amounts of matter and antimatter, which would have annihilated one another into radiation. Yet our universe clearly favors matter. Every galaxy, star, planet, and person is made from it. The grand unification epoch may hold the key to this mystery. Certain guts allow for processes that violate baryon number conservation, enabling the decay of heavy particles into more matter than antimatter. These so-called baryogenesis mechanisms remain an active area of research, as they could explain why anything solid remains at all. Yet, despite its elegance and promise, grand unification remains experimentally unverified. The energies involved are so immense that we may never reach them in a laboratory setting. Nonetheless, cosmological clues continue to emerge. Instruments like the James Webb Space Telescope, launched in December 2021, are peering deeper into the early universe than ever before, observing galaxies formed just a few 100 million years after the Big Bang. These ancient light signals carry encoded imprints of the physics that shaped the infant universe, and in them, scientists hope to uncover indirect evidence of high-energy phase transitions, inflationary dynamics, or even relics of gut-scale processes such as magnetic monopoles or proton decay. The unification of forces is more than a technical goal of theoretical physics. It is a narrative of return. We seek to trace the path of our complex universe back to its simplest, most symmetric form. Grand unification offers us a vision of the cosmos in its embryonic clarity, when forces had not yet fractured, and complexity had not yet emerged. From this unified primordial field sprang the diversity of phenomena we now observe, from galaxies and stars to atoms and life. Still, a lingering puzzle remains: gravity. Throughout the grand unification epoch, gravity loomed as an outlier. Though present from the first moments of time, gravity was not included in the unification of the other three forces. Its behavior at quantum scales remains unresolved, and theories attempting to bridge this divide, such as string theory and loop quantum gravity, are still speculative. To fully understand the pre-Planckian cosmos, we must solve this final riddle. Only then can we achieve a theory of everything, a complete unification of the four fundamental interactions. Until that day, the grand unification epoch stands as a bridge between the unknowable realm of the Planck era and the more familiar physics that governs our observable universe. It is a fleeting moment in time, a trillionth of a second, yet it represents the profound simplicity from which all complexity descends. In studying it, we not only chase the origins of matter, energy, and force, but also deepen our understanding of the universe's fundamental nature and our place within it. Inflation, the first picosecond of the universe. Among the most dramatic and revolutionary developments in modern cosmology is the theory of inflation, an epoch of exponential expansion hypothesized to have occurred within the first fraction of a second after the birth of the universe. This idea emerged not from philosophical curiosity, but from the pressing necessity to reconcile glaring inconsistencies between observation and theory, and to rescue the classical Big Bang model from internal contradictions. Though the Big Bang framework successfully explains the cosmic microwave background radiation, the expansion of the universe, and the primordial abundances of light elements. It falls short in addressing several profound anomalies observed in the large-scale structure and temperature distribution of the cosmos. The urgency of these issues became particularly vivid with the deployment of the James Webb Space Telescope, situated 1.5 million kilometers from Earth, in a stable orbit around the Sun-Earth L2 Lagrange point. This scientific marvel spent over a year undergoing deployment and calibration before it opened its golden segmented mirrors to the depths of the cosmos. When it finally turned its infrared gaze toward the farthest reaches of the observable universe, the results were startling. In data retrieved from regions corresponding to merely 200 million years after the Big Bang, astronomers discovered galaxies that were not only present far earlier than expected, but were also remarkably structured and mature in their form. This discovery sent ripples through the scientific community, prompting astrophysicist Alison Kirkpatrick to question the very foundations of galaxy formation theory, confessing in a moment of vulnerability that she lay awake at night, wondering if everything she had ever studied had been misguided. The media predictably misinterpreted this introspective moment as an indictment of the entire Big Bang theory. In reality, the discrepancy pointed not to a flawed model of cosmic origin, but to gaps in our understanding of how structures, galaxies, stars, and matter itself emerged so swiftly in the early universe. This mystery is but a fragment of a larger tapestry of problems that plagued the classical cosmological model even before the era of high-resolution telescopes. One of the most striking issues concerns the thermal uniformity of the universe. Despite being filled with localized regions of intense heat, such as the cores of stars and the freezing vacuum of interstellar space, the average temperature of the universe is astonishingly uniform in all directions. Measurements of the cosmic microwave background radiation, a relic glow from the early universe, reveal a temperature of 2.7 Kelvin that deviates by no more than a few microkelvin across the sky. Given that the universe is approximately 93 billion light-years in diameter, and that no light could have traveled between widely separated regions in the time since the Big Bang, this thermal homogeneity poses a serious challenge. It implies that distant parts of the cosmos must have been in thermal contact in the distant past, contradicting the limitations imposed by the speed of light. This conundrum, known as the horizon problem, demands an explanation that allows causal contact between regions that are now far beyond each other's light cones. Compounding this is the issue of cosmic flatness. General relativity dictates that the geometry of the universe is governed by its total energy density. A high-density universe curves positively, closing in upon itself like the surface of a sphere. A low-density universe curves negatively, spreading out like a hyperbolic saddle. Somewhere between these two extremes lies a state of perfect spatial flatness. Observations, particularly of the cosmic microwave background and large-scale structure, indicate that the universe is astonishingly flat to within a margin of error that suggests a fine-tuning beyond plausibility. Any deviation from perfect flatness in the early universe would have magnified exponentially over cosmic time. The precision required for the universe to remain so flat today is akin to balancing a pencil on its tip for billions of years, a statistical improbability that begs for deeper explanation. This dilemma is known as the flatness problem. There is yet another paradox embedded in particle physics. Many grand unified theories, which seek to unify the strong, weak, and electromagnetic forces at extremely high energies, predict the formation of magnetic monopoles. particles possessing a single magnetic pole, either north or south. Unlike electric charges, where isolated positive and negative charges exist in abundance, no such monopoles have ever been observed for magnetism. Every magnetic field we detect is a dipole, with inseparable north and south poles. Theoretically, the early universe should have produced a vast number of magnetic monopoles, but none have been detected. Their absence presents an unresolved inconsistency between theory and observation, one that standard cosmological models fail to address. It was under the weight of these cumulative anomalies that the concept of inflation was born. In December 1979, theoretical physicist Alan Guth proposed a radical hypothesis while contemplating the monopole problem. He suggested that the early universe underwent a brief but stupendously rapid phase of exponential expansion. Rather than a linear, gradual unfolding of space from a singular origin, Guth envisioned a moment when the universe expanded faster than the speed of light, not in violation of relativity, since it was space itself that expanded, not matter traveling through it. During this fleeting moment, lasting less than a trillionth of a second, the universe doubled in size dozens of times, resulting in a net increase in volume so vast that it fundamentally reshaped the structure and appearance of the cosmos. To comprehend the scale of this inflation, consider the exponential nature of doubling. If a piece of paper 1/10 of a millimeter thick were folded in half, it would double in thickness. Repeating this fold exponentially, 2 folds, 4 folds, 8 folds, yields dramatic results. By the 10th fold, the paper is as thick as a hand. By the 30th, it reaches into space. At 42 folds, the paper's height would stretch to the moon, 51 folds to the sun. At 90 folds, the thickness surpasses the span of the Virgo supercluster, 100 million light-years across. This is the metaphorical scale of the inflationary expansion Guth proposed. From a quantum speck to a galactic sea in less than a heartbeat of cosmic time. Inflation, in its breathtaking scope, solves the problems that plagued early cosmological models. It explains the thermal uniformity we observe not by asserting faster-than-light communication, but by proposing that the observable universe originated from a much smaller region that was once in causal contact and thermal equilibrium. When this compact region underwent inflation, it expanded beyond the bounds of mutual interaction, but retained the uniformity imprinted in its earlier state. In this way, inflation resolves the horizon problem without violating the laws of physics. Similarly, inflation offers a resolution to the flatness problem. By stretching any initial curvature to near zero, it renders the observable universe effectively flat. Just as the surface of a massive sphere appears flat to someone walking on it, so too does the vast, inflated universe appear geometrically neutral on the scales we can observe. What might be a curved higher-dimensional manifold is to us indistinguishable from a flat continuum. And in the case of magnetic monopoles, inflation provides a dilution mechanism. If these exotic particles did exist in the early universe, their density would have been dramatically reduced by the rapid expansion, spreading them so thinly across the cosmos that detecting even one would be statistically improbable. The observable universe may contain only a few such relics, dispersed over such immense volumes that our instruments have yet to encounter them. Underpinning this theoretical edifice is the inflaton field, a hypothetical scalar field responsible for driving inflation. Initially trapped in a metastable high-energy state, the inflaton field exerted a form of negative pressure, causing space to expand exponentially. Eventually, the field decayed into a lower energy state, releasing vast amounts of energy into the universe in a process called reheating. This marked the end of the inflationary epoch and the beginning of a hot radiation-dominated universe. During reheating, the energy stored in the inflaton was converted into a dense plasma of particles, quarks, leptons, and gauge bosons, setting the stage for the evolution of matter and radiation as we understand them. Crucially, quantum fluctuations in the inflaton field were also inflated to cosmic proportions. Originally minute and transient, these irregularities became the seeds for the large-scale structure of the universe. Regions of slightly higher or lower energy density, when magnified by inflation, formed the scaffolding around which galaxies and clusters would coalesce billions of years later. The cosmic web of filaments, voids, and superclusters finds its origin in the ephemeral jitter of quantum fields in a universe that was still younger than a trillionth of a second. With the end of inflation and the decay of the inflaton field, the universe entered the electroweak epoch. This era, lasting until around a trillionth of a second after the Big Bang, was governed by the unified electroweak force and populated by a churning sea of particles and antiparticles. Despite the presence of massless quarks and leptons, the strong nuclear force remained dormant, and gravity, while present, was largely ineffective due to the absence of massive particles. The universe was a roiling, high-energy plasma, but the laws of physics as we know them were beginning to emerge. Yet, the universe was still incomplete. Mass, the key to gravitational clumping and structural formation, had not yet arisen. The particles remained massless and unruly, immune to the long-range influence of gravity. It would take another symmetry-breaking event, the interaction with the Higgs field, to grant particles their inertia and bind them to the gravitational order that would eventually form stars, galaxies, and planets. Thus, in the brief window following the Planck and grand unification epochs, the universe underwent its most radical transformation. Inflation not only redefined the scale and structure of the cosmos, but it also laid the foundation for the physical laws that would govern its evolution. The problems that once seemed insurmountable, thermal uniformity, spatial flatness, the absence of monopoles, now appear as natural consequences of a deeper and more dynamic early universe. The inflationary model is now deeply embedded within the theoretical framework of cosmology. While many details remain unresolved, such as the precise identity of the inflaton field, the mechanism that ended inflation, and the full topology of the multiverse it suggests, the theory offers a profound and coherent narrative for the universe's first moments. It reconciles quantum physics with gravitational theory, and it opens the door to the possibility that our observable universe is but one bubble among many in a vast and eternal cosmic landscape. In this vision, the inflationary epoch stands as the moment when chaos yielded to order, when the seed of time was sown into the fertile void of the quantum realm, and when the first whisper of cosmic destiny was carried on an exponential wind. The Higgs field and the emergence of mass, the first billionth of a second. In the vast, unfolding story of the universe, there are epochs marked not by the birth of matter, nor by the shaping of galaxies, but by profound conceptual transformations, moments when nature redefines what is possible. Among these, the first billionth of a second after the Big Bang stands as a cosmological inflection point. It was in this fleeting interval that the cosmos underwent a critical phase transition, one that broke an ancient symmetry and birthed one of the most foundational properties of reality: mass. From the earliest stirrings of philosophical thought to the precision of modern physics, symmetry has held an exalted position in our understanding of the cosmos. We see it in the biological world, the bilateral symmetry of mammals, the radial harmony of echinoderms, the fractal regularity of plants. These forms are not merely aesthetic. They are energetically efficient, algorithmically simple, and evolutionarily advantageous. Nature, it seems, favors symmetry for the same reason mathematicians do. It reduces complexity while maximizing coherence. But the physical universe, too, is deeply symmetric. In the language of theoretical physics, symmetry refers to invariance, when a system remains unchanged under certain transformations. A sphere, for instance, looks the same from every angle. Likewise, physical laws retain their form whether applied in New York or on Alpha Centauri. Such invariances are not trivial curiosities. They underpin conservation laws, dictate particle interactions, and form the backbone of our most profound theories, from quantum electrodynamics to general relativity. Indeed, the early universe was a temple of perfect symmetry. At the highest energies, moments after the Big Bang, the four fundamental forces we know today were unified in a single elegant field. The cosmos was a seething cauldron of energy and possibility, yet balanced, whole, and conceptually pristine. But like all high-energy systems in thermodynamic evolution, this symmetry could not endure. As the universe expanded and cooled, it began to fracture. The symmetries that had once unified all interactions began to break, a process akin to freezing water. The fluid, continuous state giving way to a rigid, anisotropic lattice. These cosmic phase transitions, driven by energy loss and thermodynamic constraint, signaled the emergence of a new reality, one no longer governed by absolute balance, but by broken symmetry and physical diversity. The breaking of symmetry that defined the first billionth of a second was both dramatic and consequential. Following the end of cosmic inflation and the onset of the electroweak epoch, the forces of nature continued to bifurcate. The strong nuclear force had already branched off during the grand unification era. What remained was the electroweak force, a hybrid field that governed both electromagnetism and the weak nuclear interaction. Around a trillionth of a second post-Big Bang, this force too began to separate. The universe cooled to a threshold where the unified electro-weak interaction fractured into two distinct components. The electromagnetic force, mediated by the massless photon, and the weak nuclear force, mediated by the massive W and Z bosons. But this split did more than just diversify the interaction schema of the universe. It introduced an entirely new property into existence: inertial mass. This symmetry breaking did not occur passively. It was driven by the emergence of a new kind of field, a field unlike any before. This was the Higgs field, a scalar field theorized to permeate all of spacetime. According to theoretical physicist Peter Higgs and others working in the 1960s, the Higgs field did not merely exist, it shaped existence. When certain particles interacted with it, they acquired mass. Those that passed through it unimpeded, like the photon, remained massless. It was a universal viscosity, invisible and omnipresent, determining the heft of every fundamental entity in the cosmos. The mechanism by which the Higgs field grants mass is profoundly elegant. Imagine a symmetric field, initially resting at a high energy state, undergoing a spontaneous symmetry breaking as the universe cools. Like a ball rolling from the peak of a hill into one of many possible valleys, the Higgs field settles into a lower energy configuration. This choice of vacuum state breaks the symmetry, and the field begins interacting selectively with other particles. The strength of this interaction determines the mass of each particle, a subtle coupling that defines the architecture of reality. The search for the fundamental particles of matter has long captivated human inquiry. From the indivisible atomos of Democritus to the electrons and protons of the early 20th century, we have continually sought smaller, more elemental pieces of reality. By the 1970s, physicists had assembled a robust theoretical framework, the Standard Model of Particle Physics, that unified all known particles and interactions into a coherent tapestry. At its core, the Standard Model contains 12 fermions, the building blocks of matter, 6 quarks and 6 leptons. These include the up and down quarks that form protons and neutrons, the electron and its neutrino, and heavier, short-lived cousins such as the charm, strange, top, and bottom quarks, along with the muon, tau, and their respective neutrinos. Alongside these are the gauge bosons, the force carriers, photons, gluons, and W and Z bosons. And yet, there was a glaring omission in this grand framework: mass. The Standard Model, as originally formulated, could not explain why the W and Z bosons were so heavy while photons were massless. Nor could it account for the hierarchy of fermion masses, why the top quark outweighs an electron by a factor of over 300,000, or why neutrinos are so light they are barely detectable. These gaps threaten to undermine the entire edifice. The Higgs mechanism provided the missing link. It postulated that a single scalar field, the Higgs field, couples to all particles through interactions proportional to their mass. The heavier the particle, the stronger its interaction with the field. The W and Z bosons, for instance, interact intensely, explaining their considerable mass, while photons do not interact at all, remaining weightless. Electrons, quarks, and other fermions fall somewhere in between. But this theory came with a caveat. The Higgs boson, the quantized excitation of the field, had to exist. And it had to be found. Confirming the Higgs field's existence required a technological leap. To probe energies corresponding to the early universe's conditions, scientists needed colossal machines. Particle accelerators that could replicate those ancient moments. The Tevatron at Fermilab and the Large Hadron Collider at CERN became the central battlegrounds for this experimental quest. It was no easy task. The Higgs boson was expected to decay almost instantaneously into other particles, leaving behind a signature buried in the chaotic wreckage of high-energy collisions. Compounding the problem, the Standard Model offered no precise prediction for the Higgs mass, only bounds within which it might be found. It was akin to searching for an invisible needle in a haystack the size of a planet, with only the faintest ripple in the surrounding straw to mark its passage. Nevertheless, in July 2012, the physics community erupted in celebration. After years of data collection and exhaustive analysis, researchers at CERN announced the discovery of a new particle consistent with the long-sought Higgs boson. The missing piece had been found, the Standard Model was vindicated, and more importantly, the Higgs field was confirmed to be real, forever altering our understanding of the early universe. With the Higgs field activated, the cosmic phase transition was complete. The once perfect symmetry of the early universe was now irreversibly fractured, and with this fracture came form, differentiation, and substance. Particles that had floated massless through the pre-Higgs vacuum were now endowed with mass and inertia, becoming susceptible to gravitational influence and capable of forming bound structures. The electroweak force had split into two distinct interactions, mediated by different bosons of vastly different mass. The photon, exempt from Higgs coupling, remained free to travel infinite distances, laying the groundwork for electromagnetism and light. The W and Z bosons, now massively burdened, became short-range messengers of the weak interaction, central to processes such as radioactive decay. Meanwhile, quarks, now massive, began to coalesce under the strong force into hadrons, protons, neutrons, and their exotic cousins. Electrons, too, now bore mass, allowing them to orbit nuclei, setting the stage for the eventual formation of atoms. The primordial soup of quark-gluon plasma, forged in the furnace of inflation and sculpted by the Higgs, now contained all the ingredients necessary for structure. It is worth noting that even with the Higgs field's action, the origin of most mass in the universe is still not the mass of fundamental particles themselves. A proton, for example, derives more than 90% of its mass not from the quarks it contains, but from the kinetic and binding energy of those quarks and gluons within. In other words, the lion's share of mass arises from energy bound and trapped within quantum systems. Mass is, at its core, a form of confined motion, E equals mc squared given form. By the end of the first billionth of a second, the universe was transformed. The standard model particles were in place. The four fundamental forces were separated. The Higgs field had woven mass into the very fabric of the cosmos. The symmetry of the early universe had been beautifully broken, not as a flaw, but as a necessity, a gateway to complexity, to formation, and ultimately to life. The quark era had now begun in earnest. The universe, still unimaginably hot and dense, was dominated by free quarks and gluons, suspended in a high-energy plasma. But as expansion continued, temperatures dropped further. Within microseconds, quarks began to bind into protons and neutrons. Within minutes, the first atomic nuclei would form, and hundreds of thousands of years later, atoms would capture electrons, releasing the first light into a dark cosmos. Yet none of that, no stars, no chemistry, no consciousness, could have occurred without the events set in motion during the first billionth of a second. In that minuscule fraction of time, the universe broke its own symmetry, activated the Higgs field, and permitted mass to exist. Without mass, there is no gravity. Without gravity, no galaxies. Without galaxies, no stars. Without stars, no planets. And without planets, no us. What began as an abstract mathematical solution proposed by a modest physicist in the 1960s became, in time, one of the most profound discoveries in the history of science. The Higgs field is not just a component of theoretical physics. It is the invisible medium through which substance is defined. It is the unseen architecture of material being. And it all happened before the universe had even lived for a billionth of a second. Fine-tuning, protons, neutrons, and the vanishing of antimatter. The first millionth of a second. Within the first millionth of a second following the Big Bang, the universe embarked upon a journey of extraordinary refinement, an unfolding not of chaotic disorder, but of subtle calibration. While this early stage was still governed by staggering temperatures and densities, it already bore the fingerprints of balance, proportion, and, most remarkably, fine-tuning. At first glance, the cosmos in its infancy was violent and frenetic. Yet beneath the turbulence lay a tapestry of exquisite precision, a scaffolding upon which all complexity would one day emerge. As we examine this formative epoch, three major themes converge: the delicate calibration of the physical constants, the formation of composite hadronic particles, protons and neutrons, and the puzzling imbalance between matter and antimatter. Each of these elements, though distinct, is inextricably intertwined in the narrative of how a seemingly chaotic Big Bang culminated in a cosmos capable of forming stars, galaxies, and conscious observers. The universe, despite its staggering diversity, is governed by a set of fixed, immutable quantities known as the fundamental constants of nature. These values underpin all physical laws, yet they appear neither derived nor constrained by deeper principles. The speed of light in a vacuum, Planck's constant, the gravitational constant, and the fine structure constant are among these crucial numbers. They define the strength of forces, the stability of matter, and the evolution of cosmic structure. Crucially, they appear arbitrary, yet their values seem delicately chosen. This is not idle curiosity. The values of these constants directly influence the behavior of all matter and energy. Had the fine structure constant, which determines the strength of the electromagnetic interaction, differed by even a few percent, the formation of stable atoms might have been impossible. A larger value would have tightly bound electrons to nuclei, preventing chemical reactions. A smaller one would have made electron capture too feeble for atomic stability. The same holds for the gravitational constant. Were it stronger, stars would burn rapidly and collapse violently. Were it weaker, matter would remain diffuse, and star formation might never commence. Yet it is not just the strength of the fundamental forces that is finely tuned. It is also the masses of the elementary particles themselves. The masses of the up and down quarks, the electron, and the neutrinos are set at seemingly arbitrary but critical values. Why is the down quark slightly heavier than the up quark? Why does the proton weigh less than the neutron? Even the celebrated Higgs mechanism, which provides a process by which particles acquire mass, does not explain why the values are what they are. The constants are, at present, inputs not outputs of our most successful theories. As the universe cooled below 1 trillion degrees, around the millionth of a second mark, it transitioned into a phase in which quarks and gluons, once free and unbound, could finally coalesce into composite particles. This marks the onset of the hadron epoch. The formation of baryons, primarily protons and neutrons, became energetically favorable, and the strong nuclear force, mediated by gluons, forged the first stable nuclear matter. The proton, composed of 2 up quarks and 1 down quark, is a positively charged, stable hadron. The neutron, containing 2 down quarks and 1 up, is electrically neutral. Yet this compositional difference has deep consequences. The up quark carries a fractional electric charge of plus 2/3, while the down quark has minus 1/3. 2 ups and 1 down yield a net charge of plus 1, the proton. 2 downs and an up yield 0, the neutron. But this configuration is not a simple static assembly. The internal structure of protons and neutrons is a dynamic quantum sea, a frothing chaos of virtual particles. Quantum chromodynamics tells us that inside hadrons, valence quarks are constantly accompanied by a shifting menagerie of virtual gluons and transient quark-antiquark pairs. Even charm quarks, much heavier than up or down quarks, can momentarily flicker into existence inside a proton before vanishing. These fluctuations, ephemeral and probabilistic, contribute significantly to the total mass and behavior of the hadron. In fact, over 90% of the proton's mass arises not from the mass of its constituent quarks, but from the dynamic energy of the strong nuclear field that binds them. And yet, for all their complexity, these baryons began to dominate the universe's inventory. The interplay of strong and weak nuclear forces governed their formation and transmutation. The weak force, in particular, allowed for transformations between protons and neutrons via processes such as beta decay. In this way, the early universe maintained a dynamic equilibrium between these 2 building blocks of matter. But as the universe expanded, it cooled further, reducing the energy available for such conversions. Around 1 second after the Big Bang, this process began to freeze out. The ratio of protons to neutrons at that moment was no longer governed by thermodynamic equilibrium, but by the relative masses of the up and down quarks. And here, the fine-tuning of nature re-emerged. Because the neutron is slightly heavier than the proton by a margin of approximately 1.3 MeV, the final freeze-out of the weak force left the universe with a surplus of protons. The heavier neutrons, unless bound into nuclei, would decay into protons, electrons, and antineutrinos. As a result, The emerging baryonic matter of the universe skewed strongly toward protons. This imbalance, subtle though it was, had profound implications. Protons, being positively charged, interact electromagnetically and can bind with electrons to form hydrogen atoms, the foundational building blocks of all chemistry. Neutrons, by contrast, are uncharged and cannot form stable atoms alone, while neutrons do serve essential roles within atomic nuclei, providing the nuclear glue that offsets proton-proton repulsion. The proton is the fundamental unit of atomic identity. A universe in which neutrons had been favored would have been a very different place. In such a cosmos, the stability of hydrogen would have been compromised. Chemistry, based upon the diversity of atomic structures, would be nearly impossible. Without long-lived hydrogen, stars could not form, and the nuclear fusion that creates heavier elements would be absent. The universe, though filled with matter, would have remained chemically barren. Thus, the tiny difference in mass between up and down quarks, a product of some deeper mechanism yet to be uncovered, resulted in a proton-biased universe. It is this proton asymmetry that enabled the synthesis of elements, the ignition of stars, and the eventual emergence of biology and consciousness. And yet, another imbalance was unfolding during this same epoch, one no less critical and no less mysterious: the overwhelming absence of antimatter. According to our best understanding of physics, energy can be converted into matter and antimatter in equal parts. Particle-antiparticle pairs, such as an electron and a positron, or a quark and an antiquark, are expected to be created in perfect symmetry. In the early universe, such pairs would have formed abundantly, only to annihilate shortly thereafter, returning their mass to radiation. Given this perfect symmetry, one would expect a cosmic standoff. Every matter particle destroyed by its antimatter twin, leaving behind a sea of photons, but no surviving matter. But that is not what we observe. The universe we inhabit is overwhelmingly composed of matter. There are stars, planets, and galaxies, but virtually no large-scale domains of antimatter. No gamma-ray annihilation signals are observed between adjacent antimatter galaxies. No positronic halos shimmer at the edges of spiral arms. Even in high-energy astrophysical environments, antimatter remains a rarity. Where did all the antimatter go? Current models suggest that for every 1 billion antimatter particles created in the early universe, there were 1,000,000,001 matter particles. That tiny asymmetry, 1 in a billion, was sufficient to seed all the stars and galaxies we observe today. The rest annihilated into photons during the earliest moments of cosmic history. Seeking the roots of baryon asymmetry, physicists call this the baryon asymmetry problem, and despite decades of investigation, its resolution remains elusive. However, certain experimental clues and theoretical frameworks provide tantalizing suggestions. In the 1950s, physicist Qianxiang Wu conducted experiments that demonstrated parity violation in weak nuclear interactions. More specifically, certain decays exhibited a preference for left-handed particles, a clear sign that symmetry was broken in fundamental interactions. Later studies confirmed that CP symmetry, the combination of charge conjugation and parity, is also violated in certain meson decays. This CP violation introduces a potential mechanism by which matter and antimatter might be treated differently by the laws of physics. It implies that in the dense, high-energy milieu of the early universe, processes may have existed that slightly favored the production of matter over antimatter. Yet the known CP violations within the standard model are insufficient to explain the observed asymmetry. As such, physicists hypothesize the existence of additional, undiscovered processes that occurred in the early universe. One promising idea involves the role of right-handed neutrinos, hypothetical particles not currently accounted for in the Standard Model. All neutrinos observed to date are left-handed, while antineutrinos are right-handed. The absence of right-handed neutrinos and left-handed antineutrinos may suggest a deeper asymmetry. Some models propose that in the high-energy conditions of the early universe, heavy right-handed neutrinos decayed preferentially into matter, thus seeding the imbalance. This theory, known as leptogenesis, links the mystery of neutrino mass with the origin of matter. Though elegant, it remains unconfirmed. Experiments at neutrino observatories such as Dune and Hyper-Kamiokande may eventually provide clues. But for now, the origin of the matter-antimatter asymmetry remains one of the greatest unsolved problems in physics. A universe balanced on a razor's edge. By the end of the first millionth of a second, the universe had already undergone profound transformations. It had transitioned from a seething quantum plasma into a cosmos populated by protons, neutrons, and photons. The Higgs field had bestowed mass, the strong force had forged hadrons, the weak force had tipped the balance between particles, and amidst it all, the fine-tuned values of nature's constants had enabled just enough asymmetry to allow structure to form. Had any of these values been different, even slightly, we would not be here to ponder them. A slightly heavier down quark? The neutron becomes favored, hydrogen vanishes, and chemistry fails. A slightly weaker electromagnetic force? Atoms fail to bind. A bit more antimatter? Everything annihilates. It is a universe balanced on a razor's edge, calibrated not for simplicity, but for becoming. Neutrinos and primordial black holes, the first second. When we gaze into the most distant reaches of the observable universe, the light that reaches us carries with it the echoes of ancient, dramatic processes that took place billions of years ago. Among the myriad signals embedded in this cosmic light are traces of both the most elusive and the most extreme phenomena the cosmos has to offer, neutrinos and black holes. In particular, the first second after the Big Bang stands as one of the most profound periods in cosmic history, where these two contrasting but equally enigmatic entities began to shape the universe in subtle and far-reaching ways. One is a near-massless particle that almost never interacts with anything, while the other is a gravitational behemoth that consumes all that comes near. Yet both have their roots in the early conditions of our universe. At the 1 second mark, the temperature of the universe had dropped to around 10 billion degrees Celsius. This might sound inconceivably hot by everyday standards, but it represented a substantial cooling from earlier epochs where energies exceeded those of the most powerful particle accelerators by many orders of magnitude. At this stage, the basic building blocks of matter, quarks and leptons, had long since emerged, and hadrons such as protons and neutrons had stabilized into a hot plasma. The Higgs field had already endowed particles with mass. The four fundamental forces, strong nuclear, weak nuclear, electromagnetism, and gravity, had become distinct and were now operating in their current forms, albeit within conditions so energetic that their familiar behaviors were distorted. This first second is pivotal because it marks a boundary between eras of theoretical speculation and eras accessible to observational and experimental physics. For most of what occurred before this time, we rely on mathematical extrapolations, high-energy physics, and theoretical frameworks such as quantum gravity and string theory. But from this point forward, we begin to observe phenomena such as the cosmic neutrino background and gravitational imprints of primordial black holes that are, in principle, detectable and testable. Neutrinos, among the earliest particles to decouple from the rest of the matter-energy soup, emerged as one of the first cosmic messengers. In the hot and dense conditions prior to the 1-second mark, neutrinos collided frequently with electrons and positrons, preventing them from traveling freely. But as the universe expanded and cooled, these interactions weakened. Around 1 second after the Big Bang, the average energy of the surrounding particles had dropped sufficiently to allow neutrinos to decouple from matter. From that moment onward, these ghost-like particles began to stream freely across the cosmos, barely interacting with anything, leaving a subtle yet persistent signature known as the cosmic neutrino background. Although this background has not yet been directly observed, owing to the incredible difficulty of detecting low-energy, non-interacting neutrinos, it is a necessary component of our cosmological models. Its indirect effects have been inferred from patterns in the cosmic microwave background and the distribution of galaxies. If we ever develop the technology to detect the CNUB directly, it would extend our observational reach by nearly 380,000 years, providing a glimpse into a time otherwise invisible to us. Modern neutrino observatories, such as IceCube in Antarctica and Super Kamiokande in Japan, are engineered to detect higher energy neutrinos from distant astrophysical events. These instruments are marvels of engineering, utilizing massive volumes of matter, ice, water, or other dense materials to capture the fleeting signatures of a passing neutrino. By studying the paths of Cherenkov radiation created when neutrinos interact with atomic nuclei, scientists can reconstruct the neutrino's origin, energy, and flavor. These tools have already enabled the birth of neutrino astronomy, allowing researchers to study supernovae, gamma-ray bursts, and even the energetic cores of galaxies. Yet these modern detections pale in comparison to what is needed to observe the relic neutrinos of the early universe. With an estimated number density of just 300 per cubic centimeter and incredibly low energy, detecting the C neutrino would require instruments 1 billion times more sensitive than Klein ones. Projects such as Ptolemy are taking the first tentative steps in this direction, and future technological breakthroughs may eventually reveal this long silent chorus of the universe's birth. While neutrinos slipped away from the early universe with barely a trace, another entity may have taken a far more dramatic role: primordial black holes. These objects are not the result of stellar collapse, but are instead thought to have formed directly from the high-density fluctuations of the early universe. In the first second after the Big Bang, the energy density of the universe was so extreme that tiny quantum fluctuations, magnified by cosmic inflation, could have created regions of slightly higher than average mass density. If these overdensities were sufficient to overcome internal pressure and the outward momentum of cosmic expansion, they would have collapsed directly into black holes. Stephen Hawking was one of the first to explore this idea in depth. In 1971, he proposed that such primordial black holes could form within the first second of the universe, with sizes ranging from microscopic to many times the mass of our Sun. The exact mass of a PBH would depend on the timing of its formation. The later the black hole formed, the more mass it could gather. This idea provides a possible explanation for the otherwise puzzling existence of supermassive black holes at high redshifts, colossal gravitational entities that already existed when the universe was just a few 100 million years old. Galaxies such as the one hosting TON 618, with its central black hole of over 66 billion solar masses, present a challenge to our understanding of black hole growth. The standard model of stellar collapse and accretion simply doesn't offer enough time to reach such sizes, unless an initial black hole seed, such as a PBH, was already in place. PBHs may also offer insights into dark matter. In certain mass ranges, a population of primordial black holes could account for a significant fraction of the missing matter in the universe. However, observational evidence has thus far ruled out many mass windows. Microlensing surveys, such as those conducted by the Macho and Eros collaborations, have failed to detect the expected lensing effects for certain PBH mass ranges. Nevertheless, there remain gaps, especially in the intermediate and supermassive ranges, where PBHs could still plausibly exist. Some PBHs, especially those of low mass, would have evaporated by now via Hawking radiation. This quantum mechanical process allows black holes to lose mass over time, emitting particles in a thermal spectrum. The smaller the black hole, the faster it radiates until it eventually vanishes in a final burst of energy. If such evaporations occurred in the modern epoch, they could produce detectable gamma-ray bursts. Instruments like the Fermi Gamma-Ray Space Telescope have scanned the skies for such signals, but no unambiguous detections have been made so far. The search for PBHs continues on multiple fronts. Some efforts focus on gravitational waves. Mergers between primordial black holes would produce ripples in spacetime that could be captured by observatories like LIGO and Virgo. Future instruments, such as the Laser Interferometer Space Antenna, will extend our reach to lower frequency gravitational waves, potentially detecting mergers that occurred billions of years ago, if confirmed. Such events would open a new chapter in our understanding of the early universe and the role of gravity in shaping cosmic structure. Neutrinos and PBHs, though radically different in nature, converge on a singular point. They offer windows into the first second of existence. Neutrinos are relics of transparency, slipping away from the opaque universe and carrying with them a record of primordial conditions. PBHs, on the other hand, are the remnants of gravitational collapse, a process that permanently sealed away information behind event horizons. One offers subtlety, the other finality. Together, they bookend a cosmic threshold. The first second was not merely a continuation of prior processes, it was a transition from quantum chaos to thermodynamic evolution, from spontaneous symmetry breaking to observationally accessible structure. It was a time when the energy landscape of the cosmos stabilized, when particles found identity, and when the first messengers, both in form and in absence, departed on their long journey across time and space. In the great cosmic narrative, the first second stands as a prelude rich with consequence. Neutrinos, nearly invisible yet numerous, whisper across the cosmos the story of their origin. Primordial black holes, if they exist, mark the earliest gravitational imprints, frozen scars in spacetime left by quantum tremors. And as we refine our instruments and sharpen our theories, we draw ever closer to reading these signals not as mysteries, but as data, clues left behind in the wake of creation. What lies within that first second is no longer just theoretical territory. It is the emerging frontier of physics and cosmology. And it is in that frontier that the next generation of discoveries awaits, promising to illuminate not only the origins of the universe, but the very principles that govern all its subsequent evolution. Big Bang nucleosynthesis, the first minute. In a secure chamber deep beneath the Lawrence Livermore National Laboratory, a sphere of gold, no larger than a thimble, was blasted by the focused energy of 192 converging laser beams. In less than a fraction of a second, the inside of that golden cylinder reached a temperature hotter than the surface of the sun. Under the weight of that energy, a pellet of hydrogen isotopes, deuterium and tritium, was imploded, squeezed to a density and pressure reminiscent of stellar cores. And for the first time in human history, a self-sustaining fusion reaction occurred in a laboratory that released more energy than it consumed. It was a triumph nearly 7 decades in the making. But nature had mastered this process long ago, not in a lab, nor even in a star, but within the first minute of time itself. Before the first stars blinked into existence, before galaxies began their dance across the expanding void, the newborn universe was already hard at work in its role as an alchemist. In the inferno of its first moments, it forged the elements, hydrogen and helium above all, that would one day become the fuel of stars, the backbone of chemistry, and the substrate for life. And it did so, not in centuries or millennia, but in a window that spanned less than 20 minutes. In the earliest moments, the universe was too hot, too dense, and too violent for anything stable to exist. Quarks, the building blocks of protons and neutrons, swam freely in a quark-gluon plasma, colliding and ricocheting at nearly the speed of light. But as expansion gradually cooled the cosmic soup, these quarks began to bind into the first baryons, protons and neutrons. That process alone was an enormous leap in structural complexity. For the first time, the universe had matter, not merely as fleeting energy fluctuations, but as particles with identity and permanence. Yet forming these hadrons was only the beginning. What mattered next was how they would combine. And it was here that the universe began the delicate process of nucleosynthesis, the creation of atomic nuclei from the raw materials of protons and neutrons. This did not happen instantly, though protons and neutrons were abundant, and the strong nuclear force was capable of binding them together. The early universe was not yet ready. Temperatures were still too high, and the ocean of photons that permeated all of space was too energetic. Whenever two nucleons did manage to form a nucleus, say a deuteron made of one proton and one neutron, it was almost immediately blasted apart by an oncoming photon. The density of high-energy radiation was so overwhelming that for every baryon, there were over 1 billion photons. No matter how often particles fused, they were quickly undone. This period of frustration is known to physicists as the deuterium bottleneck. Deuterium, the isotope of hydrogen with one proton and one neutron, is a necessary intermediary in the formation of helium and other light elements. Without stable deuterium, the synthesis chain could not proceed. And so, for the first 3 minutes of cosmic time, despite the abundance of matter and the strength of the strong force, the creation of heavier nuclei was held back by the sheer energetic chaos of the early universe. But the cosmos was cooling. Second by second, as space expanded, the average temperature dropped. When it finally reached around 1 billion Kelvin, something changed. The photons, though still plentiful, no longer had the energy to consistently photodisintegrate deuterium. The bottleneck broke. Suddenly, deuterium nuclei could survive long enough to participate in further reactions. This small shift, almost imperceptible in the tumult of creation, triggered a chain reaction that altered the fate of the universe. Once stable deuterium existed, the floodgates opened. Deuterium fused with protons to form helium-3, or with other deuterons to form helium-4, which includes 2 protons and 2 neutrons, and is one of the most stable nuclei in the universe. Other pathways created trace amounts of tritium, lithium, and even beryllium. But the window was short. As the universe continued to expand and cool, these reactions became less frequent. Within 20 minutes, a nuclear furnace of the universe sputtered and died. The energy required to sustain fusion reactions dropped below the threshold, and the cosmos moved on. Yet in that brief interval, it accomplished something profound. By the time nucleosynthesis ended, the universe was composed of roughly 75% hydrogen and 25% helium by mass. With tiny traces of deuterium, helium-3, and lithium-7. The rest, carbon, oxygen, nitrogen, iron, and the 90 other naturally occurring elements, would have to wait for the lives and deaths of stars to be born. But the foundation had been laid. The ingredients were present: the fuel for stars, the medium for chemistry, and the seeds for complexity had all been forged. What is remarkable about this process is how well we understand it. Through nuclear physics and thermodynamic modeling, cosmologists can predict with exquisite accuracy the abundances of the light elements. And when these predictions are compared with the observed composition of the oldest stars and the interstellar medium, the match is astonishing. The helium fraction, for instance, remains nearly identical to that calculated from the conditions of the early universe, despite the passage of nearly 14 billion years. This consistency is one of the most compelling confirmations of the Big Bang theory. Yet the success of Big Bang nucleosynthesis is not merely in its predictions, but in the way it reveals the delicacy of the universe's initial conditions. Had the neutron been only slightly heavier relative to the proton, more of them would have decayed before fusion began, resulting in less helium. Had the expansion rate of the universe been marginally different, the fusion window might have opened too early or too late, altering the entire balance of elements. The nuclear binding energies, the strength of the strong and electromagnetic forces, the photon to baryon ratio, all had to fall within narrow bands to permit the creation of a chemically rich universe. It is this fine-tuning that continues to inspire awe among cosmologists. If the density of matter had been even slightly higher, the reactions would have proceeded further, converting too much hydrogen into helium. Without sufficient hydrogen, stars like our Sun would never ignite. On the other hand, if the matter had been too diffuse, then deuterium formation might never have become efficient, and fusion would have stalled before helium emerged. Either way, a universe filled predominantly with inert hydrogen or overabundant helium would likely be sterile, without complex chemistry, without stars, and without observers. As it stands, the balance struck in those first minutes was extraordinary. When stars finally formed hundreds of millions of years later, they inherited this primordial composition. It is from this mixture that stellar fusion continued the cosmic transmutation, forging heavier elements in their cores and scattering them in supernovae. The carbon in our bodies, the calcium in our bones, the iron in our blood, all these came later, but the hydrogen in the water we drink, and much of the helium that gives stars their light, was born in the first breath of time. When researchers at the National Ignition Facility successfully created a net positive fusion reaction in 2022, they were celebrating not just a technological achievement, but a connection to the universe's deepest history. The deuterium and tritium they used, hydrogen isotopes produced in minute quantities on Earth, are the same isotopes formed in the Big Bang, suspended in the cosmic plasma over 13 billion years ago. In their implosion chamber, they echoed on a microscopic scale what the universe had once achieved effortlessly on a grand scale. There is something poetic in the idea that the fusion of two simple nuclei, a proton and a neutron, could be the gateway to everything. From the tiniest combination of matter emerges the potential for stars, for life, and for thought. And it all began not in the heart of a star, but in the first minute after the universe was born. But the end of nucleosynthesis did not mean the end of nuclear potential. Though the cosmic forge had cooled, it left behind a reservoir of energy-rich matter suspended in space, an elemental legacy awaiting the gravitational sculpting of stars. The universe, now composed of simple nuclei and a bath of photons and neutrinos, had begun to resemble the version we observe today in its broadest strokes, even though no stars yet twinkled and no atoms had yet formed. The primordial matter was still a hot, ionized plasma in which electrons had no stable orbits around nuclei. Light was scattered and absorbed constantly, trapped within a fog of charged particles. Transparency, and with it the release of the cosmic microwave background, would not arrive until hundreds of thousands of years later. Still, what occurred in those first few minutes had already determined much of what was to follow. The relative abundances of hydrogen and helium, the survival of deuterium, and the scarcity of lithium and beryllium were locked into place, encoded into the composition of the cosmos. These light elements would become the fuel of the first stars, the scaffolding upon which the next stage of nuclear evolution would build. Without them, the heavy elements forged later in stellar cores and supernovae, the building blocks of planets, oceans, and living beings, could never have come into being. And, remarkably, this entire phase of cosmic history unfolded without the presence of stars, galaxies, or any large-scale structure. Gravity had not yet drawn matter into dense clumps. The universe was still largely homogeneous, a nearly featureless expanse, save for minute quantum fluctuations in density. Seeds that inflation had magnified, and which would eventually become galaxies. But at this early stage, fusion did not require complexity or structure. It only needed temperature, time, and the right ratio of particles. The laws of physics, operating without intervention, carried out the synthesis that defined the material basis of the universe. The end of primordial nucleosynthesis arrived not with a sudden halt, but with a gradual decline in reaction rates as the universe continued to cool and expand. Temperatures fell below the threshold necessary for new nuclear interactions. Deuterium and helium could no longer combine into heavier elements. The densities were too low, the average energies insufficient. Lithium and beryllium, though formed in small quantities, were not produced in significant abundance. And so the nuclear furnace of the cosmos shut down after 20 minutes, leaving behind a universe now defined by persistence rather than change. From this point forward, chemistry would wait for atoms to form. Stars would wait for gravity to collapse matter. But the most fundamental step, the emergence of elements from subatomic chaos, had already occurred. When we look at the sun and see its brilliant fusion reactions, we are witnessing a continuation of a process that began in the earliest epoch of cosmic time. And when we analyze the composition of ancient gas clouds, we are peering back into the elemental DNA of the universe, unchanged since its first breath. Even now, the proportions remain remarkably constant. Observations of the oldest stars and the most pristine regions of interstellar space reveal the same 75 to 25 mass ratio of hydrogen to helium that the equations of Big Bang nucleosynthesis predict. The deuterium abundance, sensitive to the density of ordinary matter in the early universe, matches precisely with our measurements. Lithium, slightly more uncertain, nevertheless, lies within observational constraints. The success of these predictions, made decades before precise measurements were possible, stands as a triumph of theoretical cosmology, a bridge between the mathematics of particle physics and the visible structure of the universe. And perhaps most profoundly, this phase of nucleosynthesis is universal. It occurred everywhere at once. Unlike stellar fusion, which is confined to the hearts of stars and triggered by gravitational collapse, Big Bang nucleosynthesis was cosmological in scale. Every region of the universe experienced it. Every cubic meter of space was a crucible. It is for this reason that the light elements are so uniformly distributed across the cosmos, and why they serve as a fingerprint of the universe's infancy. Wherever we look, whether to ancient stars, to distant galaxies, or to the emptiest voids, we find the same elemental story written in hydrogen and helium. There is an elegant simplicity to this process. From an undifferentiated fireball governed by quantum uncertainty, the universe cooled, stabilized, and set in motion the sequence that would eventually lead to complexity. But in its first minute, it already achieved the transition from raw energy to structured matter. It built, from the most basic ingredients, the stable nuclei that would endure for billions of years. That this happened without intervention, without external guidance, purely through the interaction of forces and particles governed by universal constants, is a testament to the profound power and order inherent in the laws of physics. And so, we return to our laboratories, attempting with lasers and magnetic confinement to replicate what the universe accomplished in its infancy. Every fusion experiment, every probe of high-energy nuclear interactions, is a footnote in a story that began long before Earth existed. When we finally achieved net positive energy from fusion in the lab, we were not discovering something new. We were rediscovering the first triumph of matter, echoing the work the cosmos had already perfected in its first fiery breath. The first molecule, first 100,000 years. Life, in all its complexity and unpredictability, is ultimately a story of chemistry. It is the chemistry of molecules interacting, bonding, and transforming across time and space that underlies every biological function. And though life as we know it has only arisen on a single rocky planet orbiting a modest star in a quiet corner of the Milky Way, its chemical foundations may have been written in the stars long before Earth even existed. Understanding how these molecular foundations formed requires a journey into the deep past of the cosmos, to an age not of biology, nor even of atoms as we know them, but to a universe only 100,000 years old. By this point in time, the initial violence of the Big Bang had long given way to relative calm. The intense nuclear reactions that dominated the first minutes of cosmic time had ended, leaving behind a universe filled with the lightest nuclei, hydrogen, helium, and traces of lithium. But these nuclei were still unbound to electrons, drifting in a sea of hot plasma, their electric charges preventing the formation of atoms, much less molecules. The universe remained a dense and brilliant fog of charged particles and photons, with temperatures far too high for stable atoms to form. And yet, amidst this charged chaos, the seeds of chemistry were being sown. As the cosmos continued to expand and cool, temperatures gradually fell toward a critical threshold. It was only once the average thermal energy of particles dropped below certain ionization potentials that electrons could begin to bind to nuclei, forming the first neutral atoms. Helium, with its uniquely high ionization energy and low reactivity, was the first to capture electrons, forming neutral helium atoms. Hydrogen, despite being more abundant, required a further drop in temperature before it could do the same. But in this narrow window between ionized chaos and atomic calm, a remarkable interaction occurred, the formation of the universe's first molecule. Known as helium hydride, this fragile molecular ion consists of a helium atom bonded to a proton. Though highly unstable and rarely encountered today, helium hydride marks the earliest instance of a chemical bond in the cosmos. Its existence is a testament to the universe's inherent tendency towards structure and complexity, even under the most primitive conditions. Theoretical predictions of helium hydride formation date back decades, with models suggesting that such a molecule could arise in the early universe once neutral helium and residual protons coexisted in sufficient abundance. The process relies on the strong electron affinity of helium ions, which, when immersed in a plasma with hydrogen ions, could steal electrons and form transient bonds. Though short-lived, these interactions paved the way for more complex chemistry to emerge as temperatures dropped further. The direct detection of helium hydride in space, however, proved to be an elusive goal. For many years, astronomers searched for its spectral signature without success. It wasn't until 2019 that researchers aboard the airborne Sophia Observatory, equipped with the far-infrared receiver GREAT, finally detected the molecule within the planetary nebula NGC 7027. This environment, with its hot, ionized gas and abundant ultraviolet radiation, mirrored in many ways the conditions of the early universe. The discovery confirmed that helium hydride could indeed form under natural cosmic conditions, validating decades of theoretical work and reinforcing our understanding of primordial chemistry. But while the molecule observed in NGC 7027 is not itself primordial, its formation mechanism strongly supports the idea that helium hydride would have been the universe's first molecule. The early cosmos, though lacking stars and planets, was replete with the ingredients and conditions necessary for such a bond to emerge. Once helium hydride appeared, it opened the door to additional molecular interactions. It could react with other protons, potentially leading to the formation of molecular hydrogen ions, and eventually to neutral hydrogen molecules as cooling continued. These simple reactions marked the beginning of a chemical evolution that would stretch across billions of years. Today, the field of astrochemistry reveals that the universe is far more chemically active than once believed. From clouds of interstellar gas to the icy shells of comets, complex organic molecules have been found in abundance. Aldehydes, alcohols, nitriles, and even amino acids have been detected in meteorites and interstellar space. These findings suggest that the precursors of life's essential molecules may not have formed exclusively on Earth, but may have been seeded across space, delivered by comets, asteroids, or even interstellar dust. Supporting this notion are the discoveries made in meteorites such as the Murchison meteorite in Australia and the Tagish Lake meteorite in Canada. These space rocks contain not only amino acids, but also nucleobases, the very building blocks of DNA and RNA. The presence of these molecules in extraterrestrial material strongly indicates that complex organic chemistry was taking place long before Earth coalesced into a planet. The origins of life, therefore, may lie not in a terrestrial primordial soup, but in a broader cosmic context. Yet it is essential to remember that the first step in this long chemical journey was the formation of the simplest possible molecule, helium hydride. Its creation marked the moment the universe shifted from a state of pure nuclear physics to one in which chemistry could take hold. Though it was a fleeting and unstable entity, helium hydride demonstrated that the universe was capable of forming bonds, of creating structure, of moving beyond chaos. From that point onward, as cooling continued, electrons settled into stable orbits around nuclei. Atoms became abundant, and more complex molecules formed. Eventually, gravity gathered these atoms into stars, and within their hearts, fusion created heavier elements. The periodic table, once confined to 3 or 4 elements, expanded. Planetary systems emerged. Water condensed. Organic molecules assembled. And somewhere, perhaps on Earth alone, or perhaps on countless worlds across the galaxy, those molecules began to organize, to replicate, and to awaken. The first molecule of the universe was not part of life. It did not swim in a cell or replicate like DNA. But it was a beginning, a quiet, momentary link in a vast chain of becoming. And in its ephemeral existence, it whispered the first lines of the chemical language that billions of years later would become the poetry of life itself. First atoms, first light, first 380,000 years. The universe, in its infancy, was not the placid tapestry of stars and galaxies we observe today. It was a seething ocean of energy, chaos incarnate, filled with a fog of blinding light and cascading particles in collision. For hundreds of thousands of years after the Big Bang, the cosmos remained opaque, not for lack of light, but for the inability of light to escape the furious interplay of matter and radiation. This was a time when photons, the very carriers of electromagnetic energy, found themselves trapped in an endless labyrinth of charged particles, bouncing incessantly off free electrons and protons, unable to travel more than a hair's breadth before being scattered again. Reason for this entrapment lay in the fundamental properties of matter and radiation at high energies. In those early epochs, temperatures soared above several thousand Kelvin. At such energies, atoms could not exist. Any attempt by a nucleus to capture an electron was immediately undone by the surrounding photons, which possessed more than enough energy to knock the electron away. The universe existed in a state of plasma, a hot, dense mix of free protons, electrons, helium nuclei, and radiation, all mingling in a turbulent sea. It was, in essence, a cosmos in gestation, awaiting the conditions necessary for atomic structure, stability, and transparency. The birth of the first atoms was not instantaneous, but gradually, driven by the relentless expansion and cooling of space. Over the course of 380,000 years, the universe's average temperature fell to around 3,000 Kelvin. At this critical threshold, the balance shifted. Photons no longer had the energy to consistently strip electrons from their nuclei. For the first time, the electromagnetic force prevailed. Electrons spiraled inward and became bound to hydrogen and helium nuclei, forming the first stable atoms. The plasma recombined into a neutral gas, and with that, the universe underwent one of its most dramatic transitions. With free electrons now bound within atoms, the primary obstacles to photon travel vanished. Light was free to stream across space, unimpeded, for the first time in cosmic history. This moment, known as recombination, marked the transition from a universe filled with a blinding, scattering mist to one that was suddenly transparent. The light released at that moment continues to travel through the cosmos to this day. Redshifted by the stretching of space over billions of years, it forms what we now detect as the cosmic microwave background, the oldest light in the universe, and the earliest image of the cosmos we can observe. The physics of this epoch is both elegant and complex. The formation of neutral hydrogen and helium atoms involved a delicate interplay of thermodynamics, quantum electrodynamics, and the expansion of space itself. As temperatures dropped, electrons were captured into quantized orbits around nuclei, emitting photons in the process. These photons, too low in energy to reionize other atoms, accumulated as a relic radiation field. The process was statistically governed by the Saha equation, and later, by the more precise Peebles model, which accounted for the finite rates of recombination and the density of the universe at the time. The release of the CMB was not merely a byproduct of recombination, but a cosmic revelation. It encoded in its slight anisotropies the primordial density fluctuations seeded during inflation. These tiny temperature differences, measured to be on the order of a few parts in 100,000, are the fingerprints of quantum perturbations inflated to macroscopic scales. Denser regions held slightly more matter, and over time, gravity amplified these overdensities, drawing in more mass and setting the stage for the formation of stars, galaxies, and the large-scale structure of the universe. The detection of the CMB stands among the most important empirical validations of the Big Bang model. In 1965, Arno Penzias and Robert Wilson, using a repurposed radio antenna in New Jersey, stumbled upon a persistent background hiss that pervaded the sky. After painstakingly eliminating every possible terrestrial source of the noise, including, famously, cleaning pigeon droppings from the antenna, they concluded that the signal was isotropic and universal. Unbeknownst to them, a team at Princeton University, led by Robert Dicke, had been preparing an experiment to detect precisely that signal, the thermal remnant of the universe's first light. Penzias and Wilson had found it first. Their discovery earned them the Nobel Prize and cemented the CMB as a pillar of observational cosmology. In the decades since, increasingly sophisticated instruments have mapped the CMB with stunning precision. NASA's COBE satellite first detected its anisotropies. The WMAP mission refined the resolution, revealing finer structures, and the ESA's Planck Observatory delivered the most detailed map to date, uncovering the minute temperature fluctuations that encode information about the universe's composition, curvature, and expansion history. These maps show a sky modeled with cold and hot spots, each corresponding to regions of slight over- and underdensity in the early universe. But the story does not end with light. The primordial plasma before recombination was not only a medium for radiation, but also for sound. Pressure waves rippled through the dense photon baryon fluid, driven by the tug-of-war between gravitational collapse and radiation pressure. These oscillations, known as baryon acoustic oscillations, traveled outward from initial density peaks like ripples on a pond. When recombination occurred, the medium changed. Photons decoupled and streamed freely, while baryonic matter was left behind, frozen in place at the wave fronts of these oscillations. The result was a preferred scale in the distribution of matter, a spherical shell of enhanced density that would later seed galaxy formation. Today, the imprint of BAOs can be seen not only in the CMB, but also in the large-scale clustering of galaxies. The characteristic scale, about 150 megaparsecs, acts as a cosmological standard ruler. By measuring this scale at different redshifts, astronomers can trace the expansion history of the universe, constrain dark energy models, and test the foundations of general relativity on cosmic scales. The first atoms and the first light gave the universe visibility, but they also gave it structure. Without recombination, there would be no CMB to observe, and no window into the state of the cosmos at that critical moment. Without atoms, there would be no chemistry, no stars, and no life. The transparency that emerged 380,000 years after the Big Bang did more than release light. It released the potential for observation, for complexity, and for the cosmos to begin writing the next chapter in its story. Even now, more than 13 billion years later, the light from recombination continues to permeate space. It is all around us, omnipresent and enduring, forming a backdrop to every observation we make. Its near uniformity is a reminder of the universe's common origin, while its subtle variations are a map of all that was to come. Every star, every galaxy, every atom in our bodies was born of the structures encoded in that first light. To study it is to peer not just into the past, but into the blueprint of reality itself. Thus, the era of recombination, though brief in the grand sweep of cosmic time, remains one of the most pivotal transitions in the history of the universe. It marked the moment when the cosmos emerged from its veil, when radiation ceased to dominate matter, and when the universe, having taken its first breath, opened its eyes to the light. Dark matter and dark energy first million years. In the grand narrative of cosmic evolution, the first million years after the Big Bang may appear uneventful compared to the explosive birth of particles and the sudden emergence of light. And yet, it was during this seemingly quiet chapter in the history of the universe that some of the most mysterious and consequential agents of cosmic structure began to assert their influence. These agents, dark matter and dark energy, are invisible, intangible, and yet profoundly influential. Though we cannot see them directly, the fingerprints they leave upon the universe are unmistakable. After the release of the cosmic microwave background radiation, approximately 380,000 years post-Big Bang, the universe entered an era of darkness. Photons, no longer scattered by free electrons, could finally traverse the cosmos freely. But the universe had yet to produce a single star. It was an age of neutrality, filled with primordial hydrogen and helium atoms drifting silently in a vast and expanding sea of cooling space. But this serenity was deceptive. The seeds of structure were already in place. Gravitational imprints laid down by fluctuations in the early universe, amplified by an unseen force, dark matter. The evidence for dark matter's existence stretches back nearly a century to when Swiss astronomer Fritz Zwicky observed an oddity in the Coma cluster of galaxies. The galaxies were orbiting each other at velocities that defied the gravitational pull expected from their visible mass. Zwicky proposed that there must be some form of dunkle materie, dark matter, providing the extra gravitational glue. Though his suggestion was initially met with skepticism, further observations in the latter half of the 20th century solidified the case. Most famously, in the 1970s, Vera Rubin studied the rotational curves of spiral galaxies and found that stars on the outskirts were rotating just as quickly as those near the center, a phenomenon inexplicable without the presence of additional unseen mass. What is remarkable is that dark matter began shaping the universe long before galaxies even existed. In the aftermath of recombination, normal baryonic matter was too hot and diffuse to collapse under its own gravity. However, dark matter, unencumbered by interactions with radiation, began to clump together far earlier. It laid down the invisible scaffolding for the universe, forming dense knots and vast filaments that would guide the collapse of gas clouds into the first stars and galaxies. Baryonic matter fell into these gravitational wells, forming luminous structures in the shadows of their dark matter halos. Though we know dark matter dominates the mass budget of the universe, outweighing ordinary matter by a ratio of about 6-to-1, its precise nature remains elusive. Several hypotheses have been proposed. One posits that dark matter is composed of machos, black holes, neutron stars, or brown dwarfs that simply emit too little light to be seen. Another, more widely accepted theory is that dark matter consists of WIMPs, hypothetical particles that interact via gravity and possibly the weak nuclear force, but not with electromagnetism. Despite intense searches in particle accelerators and deep underground detectors, WIMPs have yet to be observed. Whether dark matter is baryonic or non-baryonic, its role in the formation of structure is undisputed. By the time the universe was 1 million years old, dark matter had already shaped the distribution of matter on the largest scales. It dictated where galaxies would form, which regions would become voids, and how the intricate cosmic web would evolve. In simulations, when dark matter is included alongside ordinary matter, the resulting universe closely resembles the one we see through our telescopes. Without it, the universe would be smoother, dimmer, and far less hospitable to complexity. Yet, dark matter is only part of the story. The other unseen force that governs the fate of the cosmos emerged much later, but is no less important: dark energy. This mysterious component of the universe, which currently accounts for roughly 68% of its total energy density, was discovered only in the late 1990s. At that time, teams of astronomers studying distant Type 1a supernovae, used as standard candles due to their predictable brightness, noticed something unexpected. The supernovae appeared dimmer than they should have, implying they were farther away than expected. The universe, it seemed, was not just expanding, but accelerating in its expansion. This discovery shook the foundations of cosmology. It suggested that a repulsive force, counteracting gravity on the largest scales, was dominating the dynamics of the universe. Dubbed dark energy, this phenomenon is now understood as the primary driver of the universe's accelerated expansion. Its origin, however, remains one of the deepest mysteries in physics. Several models have been proposed to explain dark energy. One of the simplest is the cosmological constant, a term Einstein originally introduced into his equations of general relativity to achieve a static universe, though he later discarded it, believing it to be a mistake. The cosmological constant has returned with renewed relevance. It represents a constant energy density filling space uniformly, a kind of vacuum energy inherent to space itself. Another possibility is quintessence, a dynamic field that evolves over time and could change the rate of cosmic acceleration. Unlike the cosmological constant, which is fixed, quintessence could vary in strength and interact differently with matter and radiation. However, there is currently no experimental evidence to support this model, and the nature of dark energy remains speculative. Despite our lack of understanding, the effects of dark energy are observable. It stretches the fabric of space-time, causing galaxies to recede from one another at increasing speeds. This expansion alters the appearance of large-scale structures and affects the growth of cosmic formations over billions of years. The balance between dark matter and dark energy ultimately determines the fate of the universe, whether it will expand forever, slow to a halt, or collapse in a big crunch. Current data suggest we are headed toward an eternal expansion, a future in which galaxies move beyond each other's observable horizons and the night sky gradually fades to black. In this context, the first million years of the universe represent not just a transition from opacity to clarity, but from potential to structure. The interplay between dark matter and baryonic matter set the stage for everything that followed, from the formation of the first stars to the emergence of galaxies, planets, and life. Dark energy, though still dormant in that early epoch, would later rise to dominate the universe's destiny. We live in a universe composed primarily of things we do not understand. Ordinary matter, the atoms that make up stars, planets, and people, accounts for less than 5% of the total. The rest is dark matter and dark energy, invisible yet essential. These components govern the shape and fate of the cosmos, guiding its evolution from the moment it became transparent to the light that still echoes through the CMB. To uncover their nature is to illuminate the dark scaffolding of reality itself. As our instruments grow more sensitive and our theories more refined, we inch closer to unveiling the secrets that shaped the universe in its infancy. The first million years were not an interlude, but a foundation. In that dark silence, the universe prepared its canvas, and in the unseen, it defined the visible.